Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the violent birth of Earth's moon, a story written in molten rock and cosmic collision 4.5 billion years ago. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. 4.5 billion years ago, the Earth spins in darkness. The planet rotates once every 6 hours, a dizzying pace that makes the young world blur like a potter's wheel spinning too fast for human eyes to follow. No oceans exist yet. No continents rise above a global magma sea that stretches from pole to pole, unbroken by any solid ground. The surface glows cherry red with heat, a molten skin that never quite solidifies before the next bombardment tears it open again, exposing the white-hot interior beneath. Asteroids and planetesimals rain down from the debris-filled solar system, each impact adding mass and violence to the growing world, each collision a small apocalypse that reshapes the planetary surface in minutes. The Hadean Eon stretches before this restless planet like an endless fever dream, named for Hades, the ancient realm of fire and shadow. These first 500 million years of Earth's existence blur together in perpetual molten chaos. The atmosphere, if it can be called that, consists of vaporized rock and metal bleeding upward into space. A thin envelope of silicon dioxide and aluminum oxide that shimmers like heat mirages above summer asphalt. No life stirs anywhere on this world, no water pools in any basin, no wind carries seeds or spores across landscapes, because no landscapes exist beyond the endless magma sea. Only the slow arithmetic of gravity and collision, building a planet grain by grain, impact by impact, with the patient indifference of geological time. The young sun burns 30% dimmer than it will in later eons, but its rays still pierce the dusty inner solar system with pale, ancient light. Solar winds strip away the lighter elements from planetary atmospheres, leaving behind the heavy remnants of stellar nucleosynthesis iron forged in the hearts of dying stars, silicon born in the nuclear furnaces of red giants, magnesium and aluminum scattered across space by supernovae that exploded before the solar system even began to form. These are the elements that will one day form continents and ocean floors. But for now, they circulate as vapor and droplets in the endless magma sea, mixing and separating according to density and temperature in patterns that follow no earthly logic. Scientists estimate that Earth's surface temperature during the Hadean reached 200 degrees Celsius, hot enough to keep granite liquid, hot enough to turn limestone into quicklime and steam, hot enough to boil away any water that might condense from the cosmic bombardment. The planet radiates heat into space like a coal pulled from a blacksmith's forge, glowing red-hot against the cosmic dark. Yet somehow, in this furnace of creation, the world continues to accrete mass. Gravity proves stronger than heat. Collision proves more patient than vaporization. The mathematics of planetary formation unfold with geological indifference to the violence they require. The bombardment follows no schedule that human minds could recognize. Sometimes centuries pass between major impacts. Sometimes 3 asteroids strike within a single day, each one large enough to vaporize mountain ranges if mountain ranges existed to vaporize. The largest projectiles measure hundreds of kilometers across small worlds in their own right, carrying their own histories of metal and stone across the void before surrendering their mass to Earth's growing bulk. Each impact sends shockwaves through the magma ocean, creating ripples that circle the globe like slow tsunamis of molten rock. Between impacts, the surface tries to cool. Crystallization begins at the very top of the magma sea, forming thin crusts of basalt and anorthosite that float like scum on the molten surface. These first attempts at solid ground rarely last long. The next asteroid strike shatters them back into component atoms, mixing the briefly solid rock back into the global ocean of liquid stone. Only the deepest layers begin to show signs of permanence, where pressure and time work together to create the first solid foundations of what will someday become the mantle. The planet's core forms during this epoch of violence, iron and nickel sinking through the magma ocean like heavy cream settling in milk. This iron catastrophe, as geologists call it, releases enough gravitational potential energy to keep the entire planet molten for millions of additional years. The core grows layer by layer as denser materials migrate inward, following the inexorable pull of gravity that sorts matter by weight with the precision of a cosmic sieve. Somewhere in this same inner solar system, another world spins through its own Hadean nightmare. This second planet, similar in size to Mars, follows an orbital path that brings it closer to the Sun with each passing million years. Its surface tells the same story of impact and accretion, of failed crystallization and renewed melting, of metal cores forming in darkness while bombardment continues above. The gravitational dance between these two worlds grows more intricate with each orbit, their paths slowly converging toward a meeting that neither planet can avoid. The night sky above the molten Earth shows no familiar constellations. The Milky Way stretches overhead like a river of ancient light, but the patterns of stars bear no resemblance to any sky that human eyes will ever see. The solar system itself occupies a different position in the galaxy's spiral arms, and the Sun's neighborhood contains stellar companions that have long since drifted away into deep space. This is deep time made visible not just the youth of worlds, but the youth of star patterns themselves, a reminder that even the most permanent features of night sky are temporary arrangements in cosmic history. The mystery that haunts this epoch concerns the source of Earth's eventual water. The bombardment strips away volatiles as quickly as it delivers them, and the surface temperature prevents any liquid water from surviving for more than moments. Yet, somehow, in the eons that follow, oceans will appear. How they form and where their water originates remains one of the great puzzles of planetary science, a question that draws researchers back to computer models and laboratory experiments, searching for answers in the physics of vaporization and condensation. Time moves differently in the Hadean. 1,000,000 years passes like a season, marked only by the gradual cooling of the magma ocean and the slow accumulation of solid matter in the planetary interior. The young Earth exists in a state of perpetual becoming, never quite achieving the stability that will one day allow for continents and seas, life and weather, the complex chemistry of a mature world. For now, it remains a work in progress, a planet-sized furnace where the basic building blocks of terrestrial geology slowly sort themselves according to the fundamental forces of nature. In the gravitational architecture of the early solar system, a second world drifts through the darkness beyond Earth's orbit. This planet, which scientists have named Theia after the Greek Titaness who bore the moon goddess Selene, measures roughly the size of Mars, large enough to have developed its own iron core, small enough to lack the gravitational dominance that would clear its orbital neighborhood of debris. Theia follows an elliptical path around the young Sun, a trajectory that carries it through the same region of space where Earth accumulates mass from the primordial disk of dust and rock. The orbital mechanics that govern Theia's journey unfold according to Kepler's laws. Those elegant mathematical relationships that describe how worlds move through space. Theia's orbit intersects Earth's orbital path at 2 points, called nodes, where the gravitational influence of the larger planet begins to perturb the smaller world's trajectory. These perturbations accumulate over millions of years, like compound interest in a cosmic bank account, gradually altering Theia's path until collision becomes inevitable. The mathematics of celestial mechanics work with the patience of geological time, guiding two worlds toward a rendezvous that neither can escape. Theia's surface tells its own story of Hadean bombardment. Impact craters overlap like rings on water, each new collision erasing the scars of previous impacts while adding fresh wounds to the planetary crust. The world spins more slowly than Earth, completing one rotation every 24 hours, a leisurely pace that allows its molten surface to cool and crystallize between major bombardments. Thin atmospheres of water vapor and carbon dioxide rise from volcanic outgassing, only to be stripped away by solar winds and the vacuum of space. The planet exists in a state of perpetual atmospheric loss, exhaling its volatile elements into the void like a slowly deflating balloon. The composition of Theia remains a subject of scientific debate and computational modeling. Isotopic analysis of lunar samples suggests that the impacting planet formed in roughly the same region of the solar system as Earth, accreting from similar materials under similar conditions. Both worlds incorporated iron and silicate minerals in roughly the same proportions. Both experienced the same rain of water-bearing asteroids and comets. Both endured the same bombardment of leftover planetary building blocks. This compositional similarity will prove crucial to the physics of their eventual collision, determining how much material survives the impact and how much vaporizes into space. Computer simulations reveal that Theia approaches Earth not head-on, but at an oblique angle, like a billiard ball striking another ball near its edge rather than straight through its center. This glancing trajectory results from the gravitational choreography of the inner solar system, where the orbital resonances between planets create preferred angles of approach. A direct impact would likely destroy both worlds entirely, vaporizing their mass into a cloud of superheated plasma that would gradually disperse into space. The oblique angle preserves just enough material to form a satellite system, though the collision itself remains one of the most violent events in terrestrial history. As Theia spirals inward toward its appointment with Earth, the gravitational interaction between the two worlds begins to manifest in subtle ways. Earth's much larger mass perturbs Theia's rotation, creating tidal bulges in the smaller planet's molten crust that rise and fall like slow waves on a magma ocean. These tidal forces generate internal friction that converts orbital energy into heat, gradually warming Theia's interior and ensuring that both worlds remain largely molten at the moment of impact. The physics of tidal heating will play a crucial role in determining how much material survives the collision in liquid form versus how much vaporizes into plasma. The approaching collision represents a cosmic coincidence of almost impossible rarity. Computer models suggest that planetary systems capable of producing Earth-sized moons require impacts at precisely the right angle, at precisely the right velocity, between planets of precisely the right mass ratio. Too large an impactor destroys the target world entirely. Too small an impactor fails to excavate sufficient material for satellite formation. Too fast, a collision vaporizes everything into plasma. Too slow, a collision results in accretion rather than excavation. The parameters that allow moon formation occupy a narrow range in the vast space of possible planetary collisions. The mystery of Theia's origin deepens when scientists consider the dynamics of planetary migration in the early solar system. Jupiter's gravitational influence scattered smaller worlds throughout the inner solar system, sending some into the Sun and others toward the outer planets or into interstellar space. The fact that Theia survived long enough to impact Earth suggests either remarkable orbital luck or some previously unknown mechanism that protected Mars-sized planets from gravitational ejection. Recent theories propose that Theia may have formed at one of the Lagrange points in Earth's orbit, gravitationally stable regions where smaller bodies can accumulate mass without immediate collision. The timeline of Theia's approach remains constrained by the dating of lunar samples and meteorites. Radiometric analysis suggests that the moon-forming impact occurred approximately 50 to 100 million years after the formation of the solar system, during the final stages of planetary accretion when most of the large debris had already been swept up by the growing worlds. This timing places the collision near the end of the Hadean Eon, when Earth's surface had begun to show the first signs of cooling and partial crystallization. The impact would reset this geological clock, returning both worlds to a fully molten state and extending the Hadean conditions for millions of additional years. The gravitational field around Earth begins to capture some of Theia's smaller companions, asteroids and planetesimals that follow similar orbital paths through the inner solar system. These secondary impacts crater both worlds with increasing frequency as the collision approaches, like the first drops of rain before a thunderstorm. Each small impact adds energy to the Earth-Theia system, slowly increasing the relative velocity between the two planets and ensuring that their eventual collision occurs at the optimal speed for satellite formation rather than mutual destruction. Ironically, the violent collision that will create Earth's moon also represents one of the most creative events in planetary history. The impact will redistribute angular momentum throughout the Earth-Moon system, establishing the rotational dynamics that govern terrestrial day length and lunar orbital period for billions of years to come. The collision will also fractionate chemical elements according to their volatility, concentrating refractory materials in the Moon while allowing lighter elements to escape into space. These consequences of destruction become the foundations for construction, the chaos that enables future order. As Theia completes its final orbits around the Sun, the gravitational pull of Earth grows stronger with each passing perihelion. The smaller planet's trajectory bends incrementally inward, following the curved space-time around Earth's mass like a marble rolling down an increasingly steep funnel. The physics of orbital decay proceed according to precise mathematical laws, but the emotional weight of impending collision remains beyond calculation. Two worlds, each the product of 50 million years of accretion and bombardment, approach their mutual transformation with the inevitability of falling water. The last moments before impact stretch across thousands of years. As Theia's orbit decays from elliptical to parabolic to hyperbolic relative to Earth's surface, during this final approach, both planets experience extreme tidal forces that stretch and compress their molten crusts, creating massive volcanic eruptions and global lava floods that erase the final traces of their separate geological histories. The two worlds prepare for collision by returning to their most primitive molten state, as if the violence ahead requires them to forget everything they have learned about being planets. The collision begins at 11 kilometers per second, a velocity that transforms matter itself. Theia strikes Earth at an angle of approximately 45 degrees, impacting not at the equator, but at a latitude that will determine the orientation of the resulting debris disk. The first contact occurs when Theia's leading edge encounters Earth's outermost atmosphere of vaporized rock, a tenuous envelope of silicon and aluminum oxides that extends several thousand kilometers above the molten surface. This initial interaction generates a shock wave that propagates through both worlds at the speed of sound in molten silicate roughly 6 kilometers per second, meaning that the planet-wide consequences of impact arrive at Earth's antipode 17 minutes after first contact. The physics of hypervelocity impact operate according to principles that laboratory experiments can only approximate. When solid matter collides at velocities exceeding 3 kilometers per second, the materials behave more like fluids than solids, flowing and splashing according to the equations of hydrodynamics rather than the fracture mechanics that govern slower impacts. At 11 kilometers per second, both Theia and Earth's collision zone enter a regime where pressure exceeds 100 gigapascals, conditions normally found only in the deep interiors of planets or in the shock waves of nuclear explosions. Under such pressure, quartz transforms into stishovite, a dense polymorph that forms only during the most extreme geological events. The energy released by the collision equals approximately 100 million times the impact that will one day end the Cretaceous period and extinguish the dinosaurs. This energy manifests as heat, light, and kinetic motion, vaporizing approximately 10% of both planets' mass into a plasma cloud that glows white-hot against the darkness of space. The remaining 90% liquefies instantly, creating two interpenetrating spheres of molten rock and metal that merge and separate according to the complex fluid dynamics of planetary-scale collision. Computer simulations require millions of computational hours to model even simplified versions of this event, and the full physics remain beyond current mathematical description. The impact occurs in stages that unfold over approximately 24 hours of Earth time. During the first few minutes, Theia's iron core penetrates Earth's mantle like a bullet passing through gelatin, creating a cavity that temporarily disrupts the larger planet's gravitational field. The disruption sends shockwaves through Earth's molten interior, generating seismic waves that circle the globe multiple times before dissipating their energy as heat. Meanwhile, Theia's silicate mantle spreads across Earth's surface in an expanding wave of molten rock that reaches velocities of several kilometers per second, fast enough to achieve orbital velocity and escape Earth's gravity entirely. The oblique angle of impact proves crucial to the formation of Earth's satellite system. A head-on collision would drive Theia's mass directly into Earth's core, mixing the two iron cores and leaving insufficient angular momentum for satellite formation. The glancing blow instead causes much of Theia's mass to ricochet off Earth's surface, carrying with it enough rotational energy to remain in orbit rather than falling back to the planet. This transferred angular momentum spins up Earth's rotation to its post-impact rate of approximately 5 hours per day, while simultaneously injecting orbital energy into the cloud of debris that will eventually coalesce into the Moon. The collision zone reaches temperatures exceeding 8,000 Kelvin, hot enough to vaporize any known mineral, hot enough to dissociate molecules into individual atoms, hot enough to ionize the lighter elements and create a brief stellar corona around the impact site. This plasma cloud expands outward from the collision point at velocities approaching 10 kilometers per second, carrying away the most volatile elements, hydrogen, helium, carbon, nitrogen, and leaving behind a debris field enriched in the refractory materials that will form the Moon's bulk composition. The chemical fractionation that occurs during these moments of extreme temperature will determine the Moon's geochemistry for the remainder of solar system history. Scientists deduce the impact dynamics from the isotopic signatures preserved in lunar samples and terrestrial rocks. The oxygen isotope ratios in lunar minerals match those found in Earth's mantle almost exactly, indicating that the collision thoroughly mixed material from both planets before the debris disk condensed. However, the Moon's relative depletion in iron suggests that Theia's iron core merged with Earth's core rather than contributing significantly to lunar formation. These geochemical constraints provide crucial evidence for the giant impact hypothesis, while simultaneously raising new questions about the precise mechanics of planetary collision. The mystery of angular momentum conservation challenges theoretical models of the impact. The current Earth-Moon system contains less angular momentum than calculations predict should result from a Mars-sized impact at the required velocity. Either some angular momentum was lost to space during the collision, or the early Earth-Moon system subsequently lost rotational energy through some unknown mechanism. Recent computer simulations suggest that the collision may have temporarily created a binary planet system, two Earth-sized worlds orbiting their common center of mass, which later merged to form the modern Earth while ejecting the lunar material into a stable orbit. The impact generates a seismic event that would register as magnitude 15 on the Richter scale if such measurements applied to planetary collisions. The shock waves propagate through Earth's interior, reflecting off the core mantle boundary and creating interference patterns that fragment the planet's crust into a mosaic of floating plates separated by magma channels. These early tectonic processes bear little resemblance to modern plate tectonics, operating instead according to the chaotic dynamics of a world whose entire surface has been reduced to a state of turbulent flow. The atmospheric consequences of the collision extend far beyond the immediate vaporization of surface rocks. The impact ejects approximately 1 Earth mass of material into space, much of which escapes the Earth-Moon system entirely and disperses throughout the inner solar system. This material will eventually be reaccreted by Earth, Venus, and Mars over the following 100 million years, contributing to the late heavy bombardment that craters the surfaces of all terrestrial planets. The Earth temporarily loses its atmosphere entirely during the collision, requiring millions of years of volcanic outgassing to rebuild even a thin envelope of carbon dioxide and water vapor. The duration of the impact itself, approximately 24 hours from first contact to gravitational relaxation, represents one of the briefest episodes in geological time, yet its consequences shape terrestrial evolution for the following 4.5 billion years. The collision establishes Earth's final mass, determines the Moon's orbital characteristics, sets the length of terrestrial days, and creates the tidal forces that will later influence everything from ocean circulation to biological evolution. A single day of violence programs the dynamics of the Earth-Moon system for the remainder of cosmic time. Ironically, the destruction of two worlds creates the conditions necessary for the eventual emergence of life on Earth. The Moon's gravitational influence will stabilize Earth's axial tilt, preventing the extreme climate variations that would result from chaotic rotational dynamics. The tidal forces generated by lunar gravity will drive ocean circulation and create intertidal zones where early life can adapt to changing conditions. The day-night cycle established by Earth's post-impact rotation will provide the temporal framework for circadian rhythms in countless future organisms. The violence that nearly destroys Earth also prepares it for billions of years of biological innovation. The impact site itself vanishes within hours, erased by the global convection currents that redistribute the collision energy throughout Earth's interior. No permanent scar marks the location where Theia struck. No crater survives to commemorate the most important collision in terrestrial history. The evidence exists instead in the isotopic signatures of lunar rocks, in the orbital dynamics of the Earth-Moon system, in the mathematical relationships that govern planetary rotation and tidal friction. The collision leaves its signature not in geography, but in the fundamental physics that govern the world. In the immediate aftermath of the collision, the physics of matter itself transforms around the impact zone. The tremendous energy release creates what planetary scientists call a synestia, a donut-shaped cloud of vaporized and molten rock that envelops both Earth and the debris from Theia's destruction. This structure, named after the Greek goddess of the household hearth, represents a previously unknown state of planetary matter, somewhere between a traditional planet and a rotating disk of cosmic debris. The synestia extends outward from Earth's surface to approximately 3 times the distance that the Moon will eventually orbit. A vast envelope of superheated gas and liquid droplets spinning through space like a celestial hurricane made of vaporized stone. The internal structure of the synestia follows the laws of fluid dynamics scaled up to planetary proportions. At its center, Earth's molten bulk continues to rotate as a coherent body, though its surface has been completely disrupted by the impact and mixed with material from Theia's mantle. The boundary between Earth proper and the surrounding disk remains fuzzy, defined more by density gradients than by any clear interface. Pressure decreases exponentially with distance from the central mass, creating distinct zones where different minerals can condense from the vapor phase according to their boiling points and the local temperature conditions. Temperature within the synestia ranges from 4,000 Kelvin near Earth's surface to 2,000 Kelvin at the outer edge of the disk conditions, hot enough to keep most silicate minerals in vapor form, but cool enough to allow refractory compounds like aluminum oxide and calcium-aluminum inclusions to begin condensing into solid grains. These first solid particles form the nucleation sites around which larger bodies will eventually accrete, like snowflakes forming around dust motes in a terrestrial cloud. The condensation process follows the same sequence observed in meteoritic inclusions, providing a direct link between the Moon-forming impact and the broader chemistry of solar system formation. The synestia rotates as a single coherent structure, but with differential rotation that increases with distance from Earth's center. Material near the Roche limit the distance at which tidal forces from Earth overcome the self-gravity of orbiting bodies, moves faster than objects closer to the planet, creating shear zones where turbulence mixes the vaporized rock and redistributes angular momentum throughout the disk. This differential rotation prevents the immediate collapse of the outer regions back onto Earth's surface, maintaining the disk structure for thousands of years while the material slowly cools and condenses. The lifetime of the synestia depends on the competing rates of radiative cooling and gravitational collapse. Computer models suggest that the structure persists for approximately 100 years, long enough for significant chemical fractionation to occur as different elements condense at different temperatures and distances from Earth. The outer regions of the disk cool fastest, losing heat to space through thermal radiation, while the inner zones remain hot due to their proximity to Earth's molten surface and the continued bombardment of smaller debris fragments that did not achieve escape velocity during the initial impact. Within this cosmic forge, the basic architecture of the future Moon begins to take shape through the physics of accretion and orbital dynamics. Small condensed particles collide and stick together when their relative velocities remain low enough to avoid destructive impacts. The process resembles the formation of raindrops in terrestrial clouds, where microscopic water droplets merge to form larger drops that eventually become heavy enough to fall as precipitation. In the synestia, however, gravity rather than air resistance determines which particles survive long enough to grow into substantial bodies. The chemistry of lunar formation unfolds according to the thermodynamic properties of vaporized rock under extreme conditions. Elements with high boiling points, aluminum, calcium, titanium, condense first and closest to Earth, while more volatile materials, sodium, potassium, water, remain in vapor form and eventually escape the Earth-Moon system entirely. This chemical fractionation explains why lunar rocks show depletion in volatile elements compared to terrestrial basalts, and why the Moon's bulk composition closely matches that of Earth's upper mantle rather than representing a simple mixture of Earth and Theia material. The magnetic environment within the synestia remains chaotic and poorly understood. Earth's magnetic field, generated by convection in the iron core, extends outward through the debris disk. But the field lines become tangled and disrupted by the motion of ionized gas and the electromagnetic effects of the hot plasma. Charged particles spiral along these distorted field lines, creating auroral displays that would dwarf any terrestrial aurora, painting the inner solar system with sheets of colored light visible from space. The interaction between the magnetic field and the conducting plasma may also contribute to the angular momentum transport that allows material to migrate outward from Earth's surface. Scientists puzzle over the preservation of the synestia structure against the tendency for orbiting material to either fall back onto Earth or escape into space entirely. The physics requires a delicate balance between gravitational attraction, centrifugal force, and thermal pressure that maintains the disk's integrity while allowing gradual evolution toward a more traditional satellite system. Recent theoretical work suggests that the synestia may have been stabilized by feedback loops between the condensation of solid particles, the radiative cooling of the gas phase, and the gravitational torques exerted by density variations within the disk. The observational signatures of synestia formation remain beyond direct detection with current astronomical instruments, but similar structures may exist around other stars where planetary collisions occurred during the late stages of terrestrial planet formation. The discovery of hot super-Earths orbiting close to their parent stars suggests that such collisions may be common in planetary systems, potentially creating temporary synestia structures that subsequently collapse into more conventional planet-satellite configurations. The moon-forming impact may represent just one example of a universal process in planetary system evolution. The isotopic homogenization that occurs within the synestia provides crucial evidence for the giant impact hypothesis while simultaneously challenging theoretical models of the collision itself. Lunar samples show oxygen isotope ratios identical to terrestrial rocks, indicating thorough mixing of Earth and Theia material during the impact and its aftermath. However, achieving such complete isotopic equilibration requires temperatures and mixing timescales that push the boundaries of what impact models can produce. The synestia concept helps resolve this paradox by providing a mechanism for extended high-temperature processing of the impact debris. The gradual dissipation of the synestia marks the end of the most chaotic phase of lunar formation and the beginning of more conventional accretionary processes. As the structure cools and contracts, its outer regions break up into discrete clumps of molten rock that begin to orbit Earth independently. These proto-lunar bodies range in size from kilometers to hundreds of kilometers in diameter, following elliptical orbits that intersect and merge over thousands of years. The largest of these bodies becomes the core around which the final moon will accrete, while smaller fragments either merge with this central mass or spiral inward to crash back onto Earth's surface. The legacy of the synestia phase appears in the moon's internal structure and surface composition. The thorough mixing of materials within the disk creates a satellite with relatively uniform bulk composition, but subtle variations that reflect the temperature and pressure gradients present during condensation. The moon's highlands formed from the lightest minerals that floated to the surface of the early magma ocean, preserve traces of the chemical fractionation that occurred within the synestia. The Maria, filled with later basaltic volcanism, sample deeper layers that record the final stages of lunar accretion and differentiation. Ironically, this state of matter that exists for only centuries in the 4.5 billion year history of the Earth-Moon system determines many of the fundamental characteristics that define both worlds for the remainder of cosmic time. The mass ratio between Earth and Moon, the initial orbital distance and eccentricity, the chemical composition of both bodies, and the total angular momentum of the system all emerge from the physics of synestia evolution. A brief episode of exotic matter behavior programs the long-term dynamics of two worlds, demonstrating how geological processes can amplify the consequences of short-lived events across billions of years of subsequent evolution. Within the cooling synestia, the first droplets of molten rock begin to condense from the vapor like rain forming in a planetary-scale cloud. These initial condensates measure only micrometers across tiny spheres of liquid silicate that cool rapidly in the vacuum of space, their surfaces crystallizing into glass, while their cores remain molten for minutes or hours depending on their size. The condensation follows the same physical principles that govern dewdrop formation on terrestrial mornings, but scaled up to encompass vaporized mountains and liquefied continents swirling in Earth's gravitational embrace. The temperature gradient within the disk determines which minerals condense at which orbital distances from Earth's center, closest to the molten planet, where temperatures exceed 2000 Kelvin. Only the most refractory compounds can exist in solid form, calcium-aluminum inclusions, perovskite, corundum, materials that require stellar furnaces or planetary catastrophes to create. These exotic minerals, familiar to meteorite researchers but rare on Earth's surface, form the first solid matter to appear in the lunar formation environment. They drift through the superheated gas like microscopic icebergs in a sea of vaporized stone. Further from Earth's heat, where the disk temperature drops below 1800 Kelvin, common silicate minerals begin their transition from vapor to liquid to solid. Forsterite condenses first, followed by enstatite. Then anorthite, the same sequence observed in laboratory experiments on vaporized basalt. The same order preserved in the mineral assemblages of primitive meteorites. Each condensation event releases latent heat, warming the surrounding gas and creating convection currents that redistribute both energy and material throughout the disk. The physics of phase transitions, normally confined to laboratory crucibles, operate here on a scale that dwarfs terrestrial geology. The condensation process proceeds in fits and starts, controlled by the chaotic dynamics of cooling vapor and the gravitational perturbations of Earth's tidally distorted surface. Regions of the disk cool faster than others, creating temperature inversions and pressure waves that sweep through the debris cloud like atmospheric fronts on a weather map. These disturbances trigger episodes of rapid condensation that briefly illuminate the disk with the infrared glow of crystallizing minerals, followed by periods of relative quiescence when thermal equilibrium temporarily stabilizes the vapor-liquid boundary. As droplets grow larger through collision and coalescence, they begin to exhibit the effects of surface tension and rotational dynamics. Molten silicate behaves much like liquid mercury, forming nearly perfect spheres that minimize surface area while maximizing internal cohesion. The largest droplets, reaching centimeters in diameter, develop complex internal flows as their cores remain liquid while their surfaces solidify into thin crystalline shells. These temperature gradients create thermal stresses that occasionally crack the shells, allowing the molten interiors to extrude through the fractures like miniature volcanic eruptions. The orbital mechanics of the condensing material follow Kepler's laws, but with complications introduced by the non-uniform density distribution within the disk and the ongoing mass loss as lighter elements escape to space. Particles closer to Earth orbit faster than those at greater distances, creating a shearing motion that promotes collisions between objects in adjacent orbital zones. Most of these encounters occur at low relative velocities, a few meters per second, allowing the droplets to merge rather than shatter upon impact. The process resembles raindrops combining on a window, but with gravitational forces rather than surface adhesion governing the merger dynamics. The growing population of solid particles begins to influence the structure of the disk itself through gravitational feedback effects. Concentrations of condensed material create local density enhancements that perturb the orbits of nearby gas and vapor, causing spiral density waves to propagate outward through the disk like ripples on a pond. These waves redistribute angular momentum and promote the formation of gaps and rings in the debris distribution, creating the first hints of the organized structure that will eventually characterize the lunar accretion zone. Chemical differentiation occurs simultaneously with physical condensation as different elements respond to the temperature and pressure gradients according to their individual thermodynamic properties. Iron and nickel, with their high boiling points, condense readily in the inner disk but form metallic droplets that sink toward Earth's surface under gravitational influence. Aluminum and calcium create refractory compounds that remain suspended in the outer disk, while sodium and potassium stay mostly in vapor form and gradually escape the Earth-Moon system through hydrodynamic winds driven by solar radiation pressure. The isotopic signatures that will later puzzle lunar scientists begin to form during this condensation epoch. The thorough mixing of Earth and Theia material within the synestia creates isotopic homogeneity on large scales, but local variations develop as different minerals preferentially incorporate different isotopes during crystallization. These subtle chemical fingerprints will survive for billions of years, preserved in the mineral structures of lunar samples and providing future geologists with clues about the conditions that prevailed during the Moon's formation. Scientists estimate that the condensation phase lasts approximately 1,000 years, though the timescales remain uncertain due to the complex interplay between cooling rates, collision frequencies, and gravitational dynamics. Computer simulations of the process require simplifying assumptions about the disk structure and thermodynamic properties that may not accurately reflect the extreme conditions present during actual lunar formation. The models provide qualitative insights into the physics involved, but quantitative predictions remain challenging given the unprecedented nature of the phenomena being studied. The mystery of angular momentum transport within the condensing disk continues to challenge theoretical understanding. For the Moon to reach its current orbital distance, substantial amounts of angular momentum must be transferred outward from the inner disk to the outer regions, but the mechanisms responsible for this transport remain poorly constrained. Magnetohydrodynamic effects, gravitational torques from spiral density waves, and turbulent viscosity all contribute to the process, but their relative importance and efficiency depend on disk properties that cannot be directly observed or easily calculated. The transition from vapor to liquid to solid represents more than just a change of state for the materials involved. It marks the beginning of gravitational accumulation that will eventually produce a satellite massive enough to influence Earth's rotation and tidal evolution. The tiny droplets condensing from the synestia carry within their crystal structures the isotopic signatures of two destroyed worlds, while their orbital dynamics preserve the angular momentum signature of the most violent collision in terrestrial history. Matter that existed as individual atoms in the plasma cloud begins its journey toward becoming the Moon. Ironically, the most rapid cooling occurs at the outer edge of the disk, where material has the best thermal contact with the vacuum of space and can radiate heat efficiently to cosmic background radiation. This creates an inside-out condensation pattern where the coolest, most solid material orbits farthest from Earth, while the hottest, most volatile components remain closest to the planet's molten surface. The temperature inversion drives convective mixing that homogenizes the chemical composition of the condensing material, ensuring that the future Moon will be made from a representative sample of both Earth and Theia rather than preferentially incorporating material from either parent world. The condensation droplets themselves become the building blocks for larger accretionary bodies, growing through low-velocity collisions that occur when orbital dynamics bring them into contact. Each merger adds mass and gravitational attraction, accelerating the accumulation process as larger bodies become more efficient at capturing smaller ones. The mathematics of runaway accretion begin to operate, though at length, scales and timescales far removed from the asteroid belt processes where planetary scientists first discovered these phenomena. The Moon begins its existence not as a single dramatic event, but as the slow arithmetic of countless tiny collisions, each one adding its microscopic contribution to the growing satellite. The collision between Earth and Theia redistributes angular momentum throughout the emerging Earth-Moon system with the precision of a cosmic clockwork, though the mechanisms remain as elegant as they are violent. Angular momentum, the rotational equivalent of linear momentum, represents one of the fundamental conserved quantities in physics, meaning that the total amount within the system cannot be created or destroyed, only transferred between different components. Before impact, Earth possessed the angular momentum of its 6-hour rotation, while Theia carried both its own rotational energy and the orbital angular momentum of its eccentric path around the Sun. The collision transforms this rotational bookkeeping into something entirely new. The oblique geometry of the impact proves crucial to the angular momentum budget of the resulting system. A head-on collision would have converted most of the rotational energy into heat and destroyed both worlds, while a completely grazing impact would have failed to excavate sufficient material for satellite formation. The actual collision angle, approximately 45 degrees from Earth's surface, strikes the optimal balance between destruction and creation, transferring roughly 80% of the system's angular momentum to Earth's post-impact rotation, while injecting the remaining 20% into the orbital motion of the debris disk that will become the Moon. The physics of angular momentum transfer during hypervelocity impacts operates through mechanisms that laboratory experiments can barely approximate. When Theia's silicate mantle spreads across Earth's surface in the moments following contact, the flowing material carries with it the rotational signature of both worlds, mixing their individual angular momentum contributions into a new combined total. The mathematical description requires tensor calculus and fluid dynamics equations that account for the complex three-dimensional motion of liquefied rock moving at several kilometers per second across a spherical planetary surface. Earth's rotation rate increases dramatically as a result of the collision, spinning up from its pre-impact period of approximately 6 hours to a new rotation period of roughly 5 hours. This acceleration occurs because the impact adds Theia's angular momentum to Earth's existing rotational energy, like a figure skater pulling in her arms to spin faster. The faster rotation creates a more pronounced equatorial bulge in Earth's molten surface, and the enhanced centrifugal force helps support the debris disk against gravitational collapse back onto the planet. Without this rotational boost, the Moon-forming material would likely fall back to Earth within decades rather than remaining in orbit for the thousands of years required for satellite accretion. The orbital angular momentum injected into the debris disk follows the mathematical relationships discovered by Johannes Kepler 4 centuries ago. Though applied here to the exotic conditions of vaporized and molten rock orbiting a tidally disrupted planet, material in the inner portions of the disk orbits faster than material farther out, creating differential rotation that generates shear forces and turbulent mixing throughout the debris cloud. These velocity differences also promote collisions between particles in adjacent orbital zones, providing the low-speed encounters necessary for accretionary growth rather than destructive fragmentation. The conservation of angular momentum imposes strict constraints on the possible configurations of the early Earth-Moon system. If the Moon formed too close to Earth, the system would contain insufficient angular momentum to account for the current orbital separation. If the moon formed too far away, the angular momentum budget would exceed what the impact could reasonably provide. The mathematical requirements limit the moon's initial orbital distance to approximately 15,000 to 20,000 kilometers from Earth's center, roughly 1/10 of the current distance, placing the satellite well within Earth's Roche limit for solid bodies, but safely outside the limit for fluid bodies held together by self-gravity. The distribution of angular momentum within the debris disk creates a natural tendency for material to migrate both inward and outward from its initial orbital position. Conservation laws require that when some material moves inward and loses angular momentum, other material must move outward and gain angular momentum to maintain the total. This redistribution process, driven by gravitational torques and viscous friction within the disk, causes the heaviest concentrations of debris to spiral outward toward more distant orbits, while smaller particles fall back toward Earth's surface. The physics resembles the behavior of Saturn's rings, though operating on much larger spatial scales and involving molten rock rather than water ice. The timescales for angular momentum redistribution within the disk depend on the efficiency of various transport mechanisms that remain poorly understood even in contemporary astrophysical research. Turbulent viscosity, generated by shear instabilities in the rotating disk, can transport angular momentum outward over thousands of years. Gravitational interactions between forming moonlets create torques that exchange angular momentum between different orbital zones over hundreds of years. Magnetic fields threading the ionized portions of the disk may also contribute to angular momentum transport, though the strength and geometry of these fields remain highly uncertain. Scientists deduce the angular momentum evolution of the early Earth-Moon system from the current orbital dynamics and the physical constraints imposed by tidal friction over geological time, working backward from the present configuration. Theoretical models suggest that the Moon must have formed much closer to Earth than its current position and subsequently migrated outward through tidal interactions that continue today at a rate of approximately 3.8 centimeters per year. This outward spiral represents the gradual conversion of Earth's rotational energy into lunar orbital energy, mediated by the gravitational effects of ocean tides and solid Earth deformation. The mystery of missing angular momentum in the Earth-Moon system challenges current understanding of the giant impact scenario. Calculations based on the collision parameters required to produce the observed isotopic signatures suggest that the system should contain approximately twice as much angular momentum as actually measured. Either some angular momentum was lost to space during the impact and its immediate aftermath, or subsequent evolutionary processes removed rotational energy from the system through mechanisms that remain unknown. Recent research has focused on the possibility that temporary satellite systems or transient ring structures may have carried away excess angular momentum during the early phases of lunar formation. The role of angular momentum in determining the Moon's final mass demonstrates how fundamental physical principles shape the architecture of planetary systems. The debris disk can only retain material with orbital velocities appropriate for stable circular motion at specific distances from Earth. Material moving too slowly falls back to the planet's surface, while material moving too fast escapes the Earth-Moon system entirely. The narrow range of velocities that produce bound but stable orbits corresponds to a specific angular momentum distribution that, in turn, determines how much mass can be incorporated into the growing satellite. The transfer of angular momentum between Earth's rotation and the Moon's orbital motion establishes the framework for billions of years of subsequent tidal evolution. Earth's gravitational field creates bulges in the solid and liquid portions of the Moon, while lunar gravity generates corresponding tidal distortions in Earth's oceans and rocky interior. The friction associated with these cyclic deformations gradually slows Earth's rotation while accelerating the Moon's orbital motion, causing the satellite to spiral outward while terrestrial days grow longer. This process will continue until Earth becomes tidally locked to the Moon, showing the same face to its satellite just as the Moon currently shows the same face to Earth. Ironically, the violent redistribution of angular momentum during the Moon-forming impact creates the conditions necessary for the stable, long-term evolution of the Earth-Moon system. Without the precise angular momentum budget established by the collision, Earth might have captured a much smaller satellite that would have spiraled back into the planet within a few million years, or alternatively retained so much rotational energy that centrifugal forces would have prevented the consolidation of a single large moon. The cosmic coincidence that produces exactly the right amount of angular momentum transfer demonstrates how rare and remarkable the Earth-Moon system may be among planetary satellites throughout the galaxy. The angular momentum signature of the giant impact remains encoded in the current orbital dynamics of the Earth-Moon system, providing a fossil record of the collision that can be decoded through careful measurement of lunar laser ranging data and theoretical modeling of tidal evolution. Each month, as the Moon completes its orbit around Earth, it traces a path through space that preserves the memory of Theia's oblique impact 4.5 billion years ago. The mathematics of orbital mechanics serve as a form of cosmic archaeology, allowing scientists to reconstruct the details of an event that predates any direct geological evidence by billions of years. Within the cooling debris disk that orbits the molten Earth, gravity begins its patient work of architectural assembly. The countless droplets of condensed silicate, each one a microscopic sphere of crystallized magma, respond to the fundamental force that shapes all cosmic structure. Initially, their gravitational attraction remains negligible compared to their orbital motion around Earth, but as collisions merge smaller particles into larger ones, the accumulating mass gradually tips the balance in favor of self-gravity over orbital dynamics. The transition from debris disk to satellite occurs particle by particle, collision by collision, following the same mathematical principles that govern planetary formation throughout the universe. The largest condensates within the disk serve as gravitational nuclei around which smaller particles begin to accumulate. These proto-moonlets, ranging from hundreds of meters to several kilometers in diameter, possess enough mass to perturb the orbits of nearby debris through their gravitational influence. The perturbations remain subtle, at first small deflections in trajectory that bring particles into contact over thousands of years rather than immediate capture. The process resembles the formation of planetesimals in the early solar nebula, though compressed into a much smaller spatial volume and operating under the additional influence of Earth's powerful gravitational field. The physics of low-velocity accretion determine whether collisions between particles result in growth or destruction. When two molten or partially molten droplets approach each other at speeds below approximately 100 meters per second, surface tension and viscous forces dominate over kinetic energy, allowing the particles to merge rather than shatter. The collision velocity depends on the relative orbital motion of the particles and their mutual gravitational attraction, creating a narrow range of encounter geometries that promote growth. Higher velocity impacts, particularly those involving already solidified fragments, tend to produce fragmentation rather than accretion, limiting the growth rate of the largest bodies in the disk. As the proto-moonlets grow through continued accretion, their increasing mass enhances their ability to capture additional material from the surrounding disk. The gravitational cross-section, the effective target area for particle capture, scales with the square of the body's mass, creating a runaway effect where the largest objects grow fastest. This positive feedback loop, discovered through studies of asteroid formation, operates with particular efficiency in the dense environment of the lunar accretion disk, where the high particle density ensures frequent encounters between growing bodies and potential accretionary material. The temperature evolution of the accreting moon proves crucial to its subsequent geological development. Each collision between merging particles releases gravitational potential energy as kinetic energy, which then converts to heat through inelastic deformation and friction. For the largest proto-moonlets, this accretional heating maintains internal temperatures high enough to keep significant portions of their interiors molten, creating magma oceans that facilitate chemical differentiation even as the satellite continues to grow. The balance between heat generation through accretion and heat loss through radiative cooling determines whether the moon forms as a cold, undifferentiated body or a hot, layered structure. Computer simulations of lunar accretion require tracking the orbital evolution of thousands of individual particles over timescales ranging from years to millennia. The calculations must account for the three body gravitational interactions between Earth, the growing moon, and each piece of debris, while also modeling the effects of collisional damping, tidal forces, and gas drag from the residual vapor in the disk. Even with modern supercomputers, these simulations can only approximate the full complexity of the accretionary process, relying on statistical methods and simplified physics to make the calculations tractable. The orbital dynamics of the growing moon become increasingly complex as its mass approaches significant fractions of its final value. Tidal forces from Earth begin to distort the satellite's shape, creating equatorial bulges and polar flattening that influence the efficiency of further accretion. The gravitational interaction between Earth and the moon also generates orbital resonances that can either enhance or inhibit the capture of remaining debris. Depending on the specific orbital frequencies involved, these resonances create gaps and concentrations in the debris distribution, similar to the structure observed in Saturn's rings, but operating on much larger spatial scales. The chemical composition of the accreting moon reflects the thermodynamic conditions that prevailed during the condensation phase of disk evolution. Material that condenses closest to Earth, where temperatures remained highest, shows enrichment in refractory elements like aluminum, titanium, and the rare earth elements. Material from the cooler outer regions of the disk carries a higher proportion of more volatile components, though still depleted relative to solar abundances due to the extreme heating during the impact event. The radial mixing of material within the disk ensures that the moon incorporates a representative sample of both high-temperature and moderate-temperature condensates. The isotopic homogeneity observed in lunar samples requires thorough mixing of Earth and Theia material during the accretionary process. The similar oxygen isotope ratios in terrestrial and lunar rocks indicate that the debris disk achieved isotopic equilibration before solidification, possibly through continued vaporization and recondensation cycles driven by the energy release from ongoing accretional collisions. This isotopic evidence provides strong support for the giant impact hypothesis while constraining the thermal evolution of the early Earth-Moon system. The time required for lunar accretion remains one of the major uncertainties in current formation models. Analytic estimates suggest that 50 to 80% of the moon's final mass accumulates within the first 1,000 years after the impact, with the remaining material accreting over the following 10,000 to 100,000 years. However, these timescales depend sensitively on assumptions about the initial disk structure, the efficiency of angular momentum transport, and the collisional properties of the debris particles. Different computer models produce accretion timescales that vary by more than an order of magnitude, indicating the need for better understanding of the fundamental physics involved. The gravitational influence of the growing moon on Earth's rotation creates a feedback loop that affects the continued evolution of the debris disk. As the moon's mass increases, its tidal effect on Earth strengthens, causing additional energy dissipation through tidal friction that gradually slows the planet's rotation. The decreased rotational speed reduces the centrifugal support for material in the disk, causing some debris to spiral inward toward Earth, while other material migrates outward to more distant orbits. This dynamical evolution continues throughout the accretionary period, influencing both the final mass of the Moon and its initial orbital characteristics. The mystery of the Moon's relatively small iron core compared to Earth's proportional core size provides important constraints on the accretionary environment. If the Moon formed from a simple mixture of Earth and Theia material, it should contain a larger iron fraction than actually observed. The iron depletion suggests either that metallic material preferentially fell back to Earth during the disk phase, or that the impact preferentially vaporized and lost iron-rich components to space. Recent models propose that the extreme temperatures in the inner disk may have vaporized iron and allowed it to escape through hydrodynamic winds, leaving behind iron-depleted silicate material to form the Moon. The accretionary process transforms not just debris into a satellite, but chaos into order, establishing the gravitational and orbital relationships that will govern the Earth-Moon system for billions of years to come. The random motions of countless particles gradually organize into the regular elliptical orbit of a single large body, while the thermal energy of accretional collisions melts and differentiates the satellite's interior. From the perspective of deep time, the violent destruction of two worlds enables the creation of a third, demonstrating how catastrophic events can become foundational processes in planetary evolution. Ironically, the Moon's formation through gravitational accretion creates a body that will spend the rest of its existence moving away from Earth through the very same gravitational forces that brought it together. The tidal interactions that dissipate energy during the satellite's growth also drive its subsequent orbital evolution, causing the Moon to spiral outward while Earth's rotation slows. The collision that brings the worlds together ultimately ensures their separation. Though operating over timescales so vast that the process appears stationary to human observation, Earth's wounded surface begins its slow recovery from the catastrophic impact. Though the healing process will require millions of years and fundamentally alter the planet's geological character, the collision site itself no longer exists. As a recognizable feature, the oblique impact has distributed Theia's mass and energy across an entire hemisphere, creating a vast basin of churning magma that extends from the impact point to the planet's antipode. The boundary between the collision zone and unaffected crust dissolves into a gradient of decreasing shock metamorphism and thermal alteration that records the three-dimensional propagation of the impact energy through Earth's interior. The immediate aftermath leaves Earth's surface as a global ocean of molten rock several hundred kilometers deep, fed by the continued bombardment of debris falling back from the impact ejecta cloud. Each returning fragment, ranging from pebble-sized droplets to mountain-sized blocks of shattered crust, adds its kinetic energy to the thermal budget of the magma ocean and prevents the formation of any stable solid crust. The surface temperature remains above 1,500 degrees Celsius for thousands of years, hot enough to keep basalt and granite in liquid form, hot enough to maintain a thin atmosphere of vaporized silicate minerals that glows red-hot against the darkness of space. The convective patterns within Earth's post-impact magma ocean follow the complex fluid dynamics of Rayleigh-Benard convection scaled up to planetary proportions. Hot material rises from the deeper interior while cooler material sinks from the surface, creating circulation cells that span entire continents and operate on timescales of centuries to millennia. These convection currents transport both heat and chemical components throughout the magma ocean, homogenizing the composition of what will eventually become Earth's crust and upper mantle. The mixing process erases most of the original chemical signatures that might have distinguished Earth's pre-impact surface from the material contributed by Theia's destruction. The cooling rate of the magma ocean depends on the efficiency of heat loss through radiative cooling to space, a process governed by the Stefan-Boltzmann law and the emissivity of molten silicate at high temperatures. Computer models suggest that the surface temperature drops by approximately 100 degrees Celsius every 10,000 years during the initial phases of cooling, though the rate decreases as the temperature differential between surface and space diminishes. The first solid crust begins to form when surface temperatures drop below 200 degrees Celsius, creating thin rafts of crystallized basalt that float on the underlying magma like ice flows on a polar sea. These earliest attempts at crustal formation remain ephemeral and unstable. The solid basalt rafts only meters thick. Crack and founder when convective upwelling brings fresh magma to the surface, or when the return of large impact debris breaks through the fragile crystalline skin. The process resembles the formation and destruction of sea ice in a storm, with solid material constantly forming and dissolving according to the local balance between cooling and heating. Each cycle of crystallization and remelting adds to the chemical differentiation of the magma ocean as different minerals crystallize at different temperatures and either sink or float according to their density. The first permanent solid crust develops through the slow accumulation of plagioclase feldspar crystals that float to the surface of the cooling magma ocean. Plagioclase, rich in aluminum and calcium, possesses a lower density than the mafic minerals that dominate the deeper portions of the molten rock, causing it to rise through the magma column like cream separating from milk. Over thousands of years, these floating crystals accumulate into thick rafts of anorthosite, nearly pure plagioclase rock that will eventually form the lunar highlands and the earliest portions of Earth's primordial crust. The process operates according to the same physical principles observed in laboratory studies of crystallizing basalt, though extended over spatial and temporal scales that dwarf any terrestrial analog. The chemical evolution of the cooling magma ocean creates the first systematic differences in composition between different portions of Earth's surface. The earliest crystallizing minerals remove specific elements from the remaining liquid, causing the residual magma to become progressively enriched in components that prefer to remain dissolved rather than crystallize. This fractional crystallization process concentrates incompatible elements including uranium, thorium, potassium, and the rare earth elements in the final portions of magma to solidify, creating chemically evolved rocks that differ dramatically from the primitive compositions that characterized the pre-impact Earth. The formation of Earth's earliest atmosphere occurs simultaneously with crustal solidification as volcanic outgassing releases water vapor, carbon dioxide, and other volatile compounds from the cooling magma ocean. However, the surface temperature remains too high for liquid water to exist, and most of the outgassed volatiles escape to space through hydrodynamic processes driven by intense solar ultraviolet radiation. The atmospheric pressure during this epoch may have reached several times the current value, creating a dense envelope of steam and carbon dioxide that enhances the greenhouse effect and slows the surface cooling rate. The magnetic field environment around the cooling Earth remains chaotic and variable due to the disrupted state of convection in the iron core. The giant impact has stirred the core mantle boundary and altered the thermal gradients that drive magnetic field generation, creating periods of weak or absent magnetic protection alternating with episodes of unusually strong field intensity. This magnetic variability affects the retention of atmospheric volatiles and the interaction between Earth's magnetosphere and the charged particle environment of the early solar system. Scientists study the record of Earth's post-impact recovery through the geochemistry of the oldest surviving rocks and the isotopic signatures preserved in mineral inclusions that escaped subsequent metamorphic alteration. The 4.4 billion-year-old zircon crystals found in Western Australia provide glimpses of conditions during the final stages of magma ocean crystallization, suggesting that liquid water may have been present on Earth's surface much earlier than previously thought. However, the interpretation of these ancient mineral archives remains controversial, with different research groups reaching conflicting conclusions about the timing and conditions of early crustal formation. The mystery of how quickly Earth's surface cooled below the critical temperature for liquid water formation has implications for understanding the earliest possible emergence of life on the planet. If the magma ocean persisted for tens of millions of years, life's origin would necessarily be delayed until much later in Earth's history. If cooling occurred within a few million years, however, the planet could have become habitable much sooner, providing additional time for the chemical evolution that preceded biology. Current estimates place the solidification of the last magma ocean between 10 and 100 million years after the Moon forming impact, though this range reflects the substantial uncertainties in thermal models rather than precise constraints from geological evidence. The cratering record preserved on the Moon provides indirect evidence for the bombardment environment that Earth experienced during its post-impact recovery. The lunar highlands, formed during the same epoch as Earth's crustal solidification, show impact crater densities that suggest a gradually declining flux of large projectiles over the first few 100 million years of solar system history. Earth would have experienced proportionally more impacts due to its larger gravitational cross-section, indicating that crustal formation occurred in an environment of continued bombardment that repeatedly disrupted the solidification process. The tidal environment during Earth's recovery differs dramatically from modern conditions due to the Moon's much closer initial orbital distance. Tidal forces 100 times stronger than those observed today create massive deformations in Earth's molten surface, generating tidal bulges several kilometers high that sweep around the planet every few hours. These extreme tides contribute additional heating through tidal friction and create complex flow patterns in the magma ocean that influence both cooling rates and chemical differentiation. The tidal energy dissipation also accelerates the Moon's outward orbital migration during this early epoch. The transition from magma ocean to solid crust marks the end of the most chaotic phase in Earth's geological evolution and establishes the foundation for all subsequent crustal processes. The chemical differentiation that occurs during crystallization creates the first systematic variations in rock composition across Earth's surface, setting the stage for the development of continental and oceanic crust with distinctly different properties. The cooling also enables the first stable hydrosphere, providing the liquid water environment necessary for the chemical reactions that will eventually lead to the emergence of life. Ironically, the complete destruction of Earth's pre-impact crust creates the conditions necessary for the formation of a more chemically evolved and differentiated planetary surface. The thorough melting and mixing of crustal material allows gravitational and chemical forces to operate more efficiently than they could in a solid environment, producing a layered structure that reflects the fundamental properties of different rock-forming minerals. The violence that erases Earth's early geological history also provides the mechanism for writing a new and more complex geological narrative. In the gravitational embrace between Earth and its newly formed satellite, the slow dance of tidal locking begins to choreograph the future relationship between the two worlds. The Moon, born from violence and chaos, starts its existence in a state of rapid rotation, inherited from the turbulent dynamics of the debris disk from which it accreted. Initially, the satellite completes one rotation in approximately 6 hours, spinning at nearly the same rate as post-impact Earth, while orbiting the planet at a distance of roughly 15,000 kilometers, close enough that Earth would appear 15 times larger in the lunar sky than the Moon appears to terrestrial observers today. The physics of tidal forces operate through the inverse cube relationship between gravitational attraction and distance, meaning that the portion of the Moon closest to Earth experiences significantly stronger gravitational pull than the portion facing away. This differential creates a permanent deformation in the Moon's shape, stretching the satellite into a prolate ellipsoid with its long axis pointed toward Earth. The magnitude of this tidal bulge depends on the Moon's internal structure and the strength of the materials comprising its outer layers. But even solid rock deforms measurably under the extreme gravitational gradients present at such close orbital distances. The tidal bulge itself remains fixed in orientation relative to Earth while the Moon rotates beneath it, creating a complex pattern of internal stress and strain that cycles through the satellite's interior with each rotation period. The solid portions of the Moon respond to this cyclical loading like a spring that is repeatedly compressed and released, converting some of the mechanical energy into heat through internal friction and plastic deformation. This process, known as tidal heating, gradually removes rotational energy from the Moon's spin while simultaneously transferring angular momentum to its orbital motion around Earth. The rate of tidal energy dissipation depends on the efficiency of energy conversion within the Moon's interior, which in turn depends on temperature, composition, and the presence of liquid zones that can flow in response to tidal stress. During the early phases of lunar evolution, when much of the satellite's interior remains molten or partially molten due to accretional heating, tidal dissipation operates with maximum efficiency. The liquid rock flows freely in response to the changing gravitational field, creating viscous friction that rapidly converts orbital and rotational energy into heat that radiates away to space. Computer models of early tidal evolution suggest that the Moon's rotation period increases from its initial 6-hour value to approximately 12 hours within the first 10,000 years after formation, and reaches 24 hours synchronous with its orbital period around Earth within roughly 100,000 years. However, these timescales remain highly uncertain due to incomplete understanding of the Moon's internal structure and thermal evolution during the early phases of its existence. The presence of a global magma ocean would accelerate tidal locking, while a completely solid interior would slow the process significantly. The orbital consequences of tidal friction extend beyond simple spin-orbit coupling to influence the Moon's distance from Earth and the eccentricity of its orbital path. As tidal forces remove energy from the Moon's rotation, conservation of angular momentum requires that some of this energy be transferred to the satellite's orbital motion, causing it to spiral gradually outward from Earth. This outward migration occurs at an initially rapid rate of several meters per year when the Moon orbits close to Earth, then slows as the satellite moves to more distant orbits where tidal forces weaken according to the inverse cube law. The Earth experiences its own tidal deformation due to the Moon's gravitational influence, though the effects remain less dramatic due to the planet's much larger mass and correspondingly smaller tidal bulges. Nevertheless, the solid Earth deforms by several meters in response to lunar gravity, creating cyclical stress patterns that generate seismic energy and contribute to the overall energy budget of tidal dissipation. The efficiency of tidal energy loss in Earth's interior depends on the presence of liquid zones, particularly the post-impact magma ocean that can flow in response to the Moon's gravitational field. The synchronized rotation that results from tidal locking ensures that the Moon will always show the same hemisphere toward Earth. Though the exact orientation depends on the details of the locking process and any subsequent perturbations from other gravitational influences, The hemisphere that faces Earth during the final phases of tidal evolution will experience a different thermal and impact history than the far side, creating the first systematic differences in lunar geology that will persist throughout the satellite's subsequent evolution. The near side will be preferentially heated by Earth's thermal radiation and shielded from some cosmic impacts by Earth's gravitational influence. The tidal heating generated during the locking process contributes significantly to the Moon's early thermal budget, potentially maintaining molten conditions in the lunar interior for millions of years longer than would result from accretional heating alone. This extended period of high internal temperatures facilitates chemical differentiation and may drive volcanic processes that resurface portions of the lunar crust. The additional heating also affects the timing of magnetic field generation in the Moon's core, if such a field ever existed. By influencing the thermal evolution of the lunar interior, scientists infer the history of tidal evolution in the Earth-Moon system from the current orbital characteristics and theoretical models of energy dissipation over geological time. The Moon's present orbital distance of 384,400 kilometers and orbital period of 27.3 days represent the cumulative result of 5 billion years of tidal friction, during which the satellite has migrated outward from its initial close orbit, while Earth's rotation has slowed from its post-impact rate of 5 hours per day to the current 24-hour period. Working backward from these present conditions allows researchers to reconstruct the probable timeline of early tidal evolution. The mystery of tidal dissipation efficiency in the early Earth-Moon system challenges current understanding of energy loss mechanisms in planetary bodies. Theoretical calculations based on laboratory measurements of rock properties under tidal stress predict much slower rates of tidal evolution than appear necessary to produce the observed orbital configuration within the age of the solar system. Either the early Earth and Moon possessed internal structures that enhanced tidal dissipation beyond current theoretical predictions, or additional energy loss mechanisms operated during the early phases of the system's evolution. The resonant interactions between Earth's rotation and the Moon's orbital motion create complex patterns of energy exchange that can either accelerate or decelerate the tidal evolution depending on the specific frequency relationships involved. When the ratio between Earth's rotation period and the Moon's orbital period approaches simple integer values, resonant coupling enhances the efficiency of angular momentum transfer and can cause rapid changes in both the planet's rotation rate and the satellite's orbital characteristics. These resonances may have played crucial roles during specific epochs of early Earth-Moon evolution. The influence of solar tides on the Earth-Moon system introduces additional complexity to the tidal evolution process, though the solar effects remain much weaker than the lunar tides due to the Sun's greater distance. However, the gravitational influence of the Sun on the Moon's orbit creates periodic variations in orbital eccentricity and inclination that modulate the strength of Earth-Moon tidal interactions over long time scales. These solar perturbations may have influenced the rate of tidal evolution during specific periods when resonant relationships enhance their effects. The development of tidal locking represents more than just a mechanical process. It establishes the foundation for the Moon's role as a stabilizer of Earth's axial tilt and rotation rate over geological time. Once locked in synchronous rotation, the Moon becomes a gravitational anchor that resists perturbations to Earth's rotational dynamics from impacts, atmospheric effects, and other planets' gravitational influences. This stabilizing effect proves crucial for maintaining relatively stable climate conditions that facilitate the emergence and evolution of life on Earth's surface. Ironically, the tidal forces that lock the Moon into synchronous rotation with Earth also ensure the satellite's eventual escape from the Earth-Moon system, though over timescales that exceed the projected lifetime of the Sun. The continued outward migration, driven by tidal friction, will eventually carry the Moon beyond Earth's gravitational sphere of influence, ending the partnership that began with the violent collision between Earth and Theia. The process that creates the stable Earth-Moon system also contains the seeds of its ultimate dissolution, demonstrating how even the most fundamental astronomical relationships remain temporary arrangements in the context of cosmic time. As the Earth-Moon system settles into its new gravitational equilibrium, both worlds begin the long process of cooling from their state of molten chaos toward the solid surfaces that will define their geological character for billions of years to come. The Moon, smaller and lacking an atmosphere to trap heat, radiates its thermal energy into the vacuum of space with the efficiency of a perfect blackbody, its surface temperature dropping according to the Stefan-Boltzmann law that governs thermal radiation from hot objects. Earth, despite its larger thermal mass and residual atmospheric envelope of vaporized rock, also begins to lose the enormous heat content generated by the collision and subsequent accretion. The lunar magma ocean cools from the outside in, following the same pattern observed in terrestrial lava lakes, but scaled up to encompass an entire world. The first solid crust forms at the surface where contact with the vacuum of space allows maximum heat loss through radiation. This initial crystallization produces a thin shell of anorthosite, nearly pure plagioclase feldspar that forms when the lightest minerals float to the top of the cooling magma and accumulate into a coherent crust. The anorthositic highlands that will dominate the lunar landscape for the remainder of solar system history begin as a scum of crystallized aluminum-rich minerals floating on a global ocean of molten rock. The cooling rate of the lunar magma ocean depends critically on the efficiency of heat transport from the deep interior to the radiating surface. Convection within the molten rock carries thermal energy upward much more efficiently than conduction through solid material, maintaining relatively uniform temperatures throughout the liquid portions of the Moon while the solid crust gradually thickens from above. Computer models suggest that the lunar magma ocean requires between 10 and 100 million years to solidify completely, though the exact timeline depends on poorly constrained parameters such as the initial temperature distribution and the thermal properties of crystallizing minerals. Earth's cooling process proves more complex due to the planet's larger size, stronger gravitational field, and the presence of a substantial atmosphere generated by outgassing from the cooling magma ocean. The atmospheric greenhouse effect traps thermal radiation and slows the surface cooling rate, while the higher pressure at Earth's surface raises the melting points of silicate minerals and requires lower temperatures for crystallization to begin. Additionally, the continued bombardment of debris returning from the impact ejecta cloud adds thermal energy to Earth's surface and periodically remelts portions of the forming crust. The chemical differentiation that occurs during magma ocean crystallization establishes the basic compositional structure of both worlds' interiors and surfaces. On the Moon, the low-density plagioclase crystals rise to form the highlands crust, while denser minerals like olivine and pyroxene sink toward the interior to form the mantle. The final portions of magma to crystallize become enriched in incompatible elements that prefer to remain in liquid rather than enter crystal structures, creating creep-rich rocks, potassium, rare earth elements, phosphorus that will later be detected in lunar samples and provide crucial insights into the Moon's formation and evolution. Earth's larger size allows for more complex differentiation processes, including the formation of distinct crustal, mantle, and core regions with different chemical and physical properties. The iron core, already partially formed before the giant impact, completes its differentiation as dense metallic material continues to sink through the molten silicate mantle. The release of gravitational potential energy during this iron catastrophe provides additional heat that extends the lifetime of Earth's magma ocean and drives continued chemical evolution of the planetary interior. The formation of the first stable atmospheres around both worlds occurs through volcanic outgassing as volatile compounds trapped in the cooling magma escape to the surface. However, the atmospheric evolution follows dramatically different paths due to the contrasting gravitational fields and thermal environments of the two bodies. Earth's stronger gravity retains most outgassed volatiles, while the Moon's weak gravitational field allows most atmospheric components to escape to space over timescales of thousands to millions of years. The cratering environment during the magma ocean cooling epoch reflects the continued bombardment from debris left over from planetary formation processes. The Moon's lack of atmosphere means that even small projectiles reach the surface at full cosmic velocity, creating impact craters that provide a permanent record of the bombardment flux during this early period. Earth's emerging atmosphere begins to screen out the smallest impactors, but larger projectiles continue to penetrate to the surface and contribute to the thermal budget of the cooling magma ocean. The magnetic field environment around both worlds remains weak or absent during the magma ocean phase due to the lack of organized convection in their iron cores. Earth's core convection may be suppressed by the thermal boundary layer created by the overlying magma ocean, while the Moon's much smaller core may lack sufficient thermal energy to drive vigorous convection at all. The absence of strong magnetic fields means that both worlds remain vulnerable to atmospheric stripping by solar wind particles and cosmic radiation. Scientists study the record of magma ocean cooling through the mineralogy and chemistry of samples returned from both worlds. Lunar samples provide direct evidence for the anorthositic highlands crust and the creep-enriched final crystallization products, while terrestrial rocks preserve isotopic signatures and trace element patterns that reflect early Earth's differentiation. However, the interpretation of these ancient chemical signatures remains challenging due to the subsequent 4.5 billion years of geological evolution that has modified or destroyed most direct evidence of early crustal formation. The mystery of how quickly life could have emerged on Earth depends critically on the timing of magma ocean solidification and the establishment of liquid water oceans. If surface temperatures remained above the boiling point of water for tens of millions of years, the origin of life would necessarily be delayed until much later in Earth's history. Recent research suggests that liquid water may have been present on Earth's surface within 100 million years of the Moon forming impact, providing a relatively early window for the chemical evolution that preceded biology. The thermal evolution of both worlds during the cooling phase determines their subsequent geological activity and surface modification processes. The Moon's small size and efficient heat loss to space lead to relatively rapid cooling and the cessation of major geological activity within the first billion years of lunar history. Earth's larger thermal mass and the insulating effect of its atmosphere allow continued geological activity, including plate tectonics, volcanism, and crustal recycling that persist throughout geological time. The establishment of solid crusts on both worlds marks the beginning of impact crater preservation and the accumulation of geological records that can be studied by future generations of scientists. The lunar highlands preserve a relatively complete record of early solar system bombardment, while Earth's more dynamic geology continuously erases and recreates its surface features. The contrast between lunar preservation and terrestrial recycling provides complementary perspectives on early solar system evolution. The cooling of the magma oceans also initiates the first systematic chemical exchanges between the solid surfaces and any residual atmospheres. Outgassing from crystallizing minerals contributes water vapor, carbon dioxide, and other volatile compounds to the atmospheric inventories, while atmospheric interaction with hot surfaces drives chemical weathering reactions that begin to modify crustal compositions. These early atmosphere-surface interactions establish precedents for the more complex biogeochemical cycles that will later characterize Earth's climate system. The end of the magma-ocean epoch represents a fundamental transition in the character of both worlds, from the chaos and uniformity of global melting to the order and diversity of solid surface geology. The crystallization of the last liquid rock creates distinct crustal provinces with different compositions, ages, and thermal histories that will influence geological processes for billions of years to come. The violent beginning that melted two entire worlds evolves into the stable platform necessary for the emergence of complexity, life, and eventually consciousness capable of understanding the cosmic events that shaped these worlds. Ironically, the complete melting and recrystallization of both worlds creates more organized and differentiated planetary structures than existed before the collision. The gravitational sorting of materials according to density and the chemical fractionation driven by crystallization processes produce layered interiors and compositionally diverse crusts that enable the complex geological processes characteristic of mature planets. The destruction of simpler, more primitive planetary structures becomes the foundation for the architectural complexity that defines the modern Earth-Moon system. In the aftermath of the collision and the gradual cooling of both worlds, the most volatile elements begin their inexorable escape from the Earth-Moon system. Stripped away by solar winds and the fundamental physics of atmospheric loss that governs all planetary bodies, water vapor, hydrogen, helium, and the noble gases rise through the thin atmospheres of both worlds, reaching escape velocities that carry them beyond the gravitational reach of Earth and Moon alike. This process of atmospheric escape operates continuously but with varying efficiency depending on the thermal energy of atmospheric particles, the strength of each world's gravitational field, and the intensity of solar radiation that drives hydrodynamic outflow from the upper atmosphere. The mechanisms of atmospheric escape follow well-established physical principles, though their application to the extreme conditions following the moon-forming impact pushes theoretical models beyond their normal operating ranges. Thermal escape, also called Jeans escape, occurs when individual atmospheric molecules acquire enough kinetic energy through random thermal motion to exceed the escape velocity for their altitude above the planetary surface. The rate of thermal escape depends exponentially on the ratio between atmospheric temperature and molecular mass, meaning that light elements like hydrogen and helium escape preferentially, while heavier species like carbon dioxide and water vapor remain gravitationally bound for longer periods. The solar wind environment during the early phases of solar system evolution proves far more intense than the relatively benign conditions observed today. The young sun produces enhanced particle fluxes and more energetic solar flares that interact directly with planetary atmospheres, particularly those lacking strong magnetic field protection. When high-energy solar wind protons collide with atmospheric molecules, they can impart sufficient momentum to drive particles above escape velocity through a process called sputtering. This non-thermal escape mechanism operates independently of atmospheric temperature and can remove even relatively heavy atmospheric components when solar activity reaches extreme levels. The Moon's weak gravitational field makes it particularly vulnerable to atmospheric loss through all escape mechanisms. With an escape velocity of only 2.4 kilometers per second compared to Earth's 11.2 kilometers per second, the Moon cannot retain any substantial atmosphere over geological timescales. Water vapor outgassed from the cooling lunar magma ocean escapes to space within thousands of years, carrying with it hydrogen and oxygen isotopes that provide clues about the volatile inventory of the original Earth-Moon system. The rapid atmospheric loss from the Moon ensures that it will remain essentially airless throughout its subsequent evolution, Earth's stronger gravitational field provides better atmospheric retention, but the extreme temperatures and enhanced solar activity during the post-impact epoch drive massive hydrodynamic escape that removes much of the planet's early atmospheric inventory. Computer models suggest that Earth may have lost several Earth masses worth of atmospheric material during the first 100 million years following the Moon-forming impact, including most of the water vapor initially outgassed from the cooling magma ocean. This massive atmospheric loss helps explain why Earth's oceans show isotopic signatures that differ from the bulk composition of carbonaceous chondrite meteorites, which are thought to represent the original building materials of the terrestrial planets. The isotopic fractionation that occurs during atmospheric escape provides a permanent record of volatile loss processes that can be decoded from the composition of atmospheric and crustal reservoirs preserved on both worlds. Light isotopes escape more readily than heavy isotopes due to their higher thermal velocities, causing the remaining atmospheric inventory to become progressively enriched in the heavier isotopic species. The degree of isotopic fractionation depends on the total fraction of the atmosphere that has been lost, allowing scientists to estimate the magnitude of atmospheric escape from isotopic measurements of ancient rocks and minerals. The loss of water vapor from both worlds during this epoch has profound implications for their subsequent evolution and habitability. Earth must reacquire its water inventory from later bombardment by comets and water-rich asteroids, while the Moon remains permanently desiccated. The timing and source of Earth's water delivery remain active areas of research, with different models proposing either early reaccumulation within 100 million years of the impact or delayed delivery during the late heavy bombardment approximately 4 billion years ago. The escape of noble gases provides particularly valuable constraints on atmospheric evolution because these chemically inert elements participate only in physical processes like outgassing and escape, without the complications introduced by chemical reactions or biological cycling. The noble gas inventories of Earth's atmosphere show clear evidence of massive early atmospheric loss, with xenon showing the most extreme isotopic fractionation due to its intermediate mass that makes it particularly sensitive to hydrodynamic escape processes. The Moon's complete lack of retained noble gases confirms the efficiency of atmospheric stripping from small planetary bodies. The solar-wind interaction with escaping atmospheric material creates a complex environment of charged particles and electromagnetic fields around both worlds. Earth's emerging magnetosphere begins to provide some protection against direct solar wind bombardment as convection in the cooling core generates the first organized magnetic fields, but the field strength remains weak and variable during the early phases of planetary evolution. The Moon never develops significant magnetic protection, leaving its surface and any residual atmosphere exposed to the full intensity of solar particle bombardment. The chemical consequences of volatile loss extend beyond simple atmospheric depletion to influence the bulk composition and subsequent geological evolution of both worlds. The preferential escape of hydrogen relative to oxygen creates oxidizing conditions in any remaining atmospheric water vapor, while the loss of carbon species affects the carbon dioxide content of early atmospheres. These compositional changes influence the efficiency of greenhouse warming, the pH of early oceans, and the chemical environment for early biological evolution on Earth. Scientists study ancient atmospheric compositions through the analysis of fluid inclusions trapped in mineral crystals, isotopic signatures in ancient rocks, and the noble gas inventories of meteorites that sample different reservoirs in the early solar system. However, the interpretation of these proxy records remains challenging due to the multiple processes that can modify volatile inventories over geological time. The relative contributions of impact-driven loss, solar wind stripping, and thermal escape to the total volatile budget remain subjects of ongoing research and debate. The mystery of Earth's atmospheric evolution during the Hadean Eon includes the question of whether the planet experienced multiple episodes of atmospheric loss and regeneration through volcanic outgassing. Some models propose that Earth's early atmosphere was completely stripped away by the moon-forming impact and subsequent solar-wind interaction, requiring the planet to rebuild its atmospheric inventory from scratch through volcanic processes. Other models suggest that portions of the original atmosphere survived in gravitationally bound reservoirs and contributed to the composition of later atmospheric evolution. The timing of atmospheric escape relative to the cooling of Earth's surface determines whether liquid water could have existed during the earliest phases of terrestrial evolution. If atmospheric stripping occurred rapidly while surface temperatures remained above the boiling point of water, then Earth's surface would have been both dry and hot for extended periods. If atmospheric regeneration through volcanic outgassing occurred more rapidly than escape processes, then liquid water oceans could have formed much earlier in Earth's history than previously thought. The efficiency of volatile escape from the Earth-Moon system influences the likelihood that similar planetary collisions in other stellar systems could produce habitable worlds with substantial water inventories. If giant impacts systematically strip away most volatile elements from terrestrial planets, then Earth-like worlds may be much rarer in the galaxy than previously estimated. Conversely, if volatile loss can be minimized through specific collision geometries or stellar environments, then Earth analogs may be more common than current models suggest. The escape of volatile elements from the early Earth-Moon system represents more than just atmospheric loss. It constitutes a fundamental reset of the chemical environment that shapes all subsequent planetary evolution. The collision that creates the Moon also erases most of the original volatile inventory of both worlds, requiring them to reacquire their atmospheric and hydrospheric reservoirs through processes that operate over much longer timescales than the impact itself. The violence that brings the Earth-Moon system into existence also strips away the chemical components necessary for life, creating a sterile environment that must be slowly repopulated with the molecules of biology. Ironically, the loss of the original volatile inventory may have been necessary for Earth's eventual habitability by removing atmospheric components that would have created runaway greenhouse conditions or chemical environments hostile to biological evolution. The atmospheric stripping that initially sterilizes Earth also provides an opportunity for the planet to rebuild its atmospheric composition through processes that create more favorable conditions for the emergence and evolution of life. The destruction of one chemical environment enables the construction of another, more suitable for the complexity that will eventually emerge on the planetary surface. The bombardment that sculpts both Earth and Moon during their earliest epochs continues with relentless persistence, though at gradually diminishing intensity as the solar system slowly sweeps up the debris left over from planetary formation. Asteroids ranging from pebbles to small mountains rain down upon both worlds, each impact adding its kinetic energy to surfaces still warm from their violent birth. The Moon, lacking any atmospheric protection, receives the full force of these cosmic projectiles, while Earth's emerging atmosphere begins to screen out the smallest fragments, though larger bodies continue to penetrate through the thin envelope of carbon dioxide and water vapor to strike the cooling surface below. The physics of hypervelocity impact operates according to scaling laws that relate crater size to projectile mass, velocity, and target material properties. When a cosmic projectile strikes a planetary surface at typical encounter velocities of 15 to 25 kilometers per second, the kinetic energy release exceeds that of chemical explosives by factors of thousands, vaporizing both the impactor and substantial volumes of target rock in a fraction of a second. The resulting explosion excavates circular craters with diameters roughly 10 times larger than the original projectile. distributing pulverized rock across hundreds of kilometers of surrounding terrain in complex patterns that reflect the physics of ballistic trajectories and shockwave propagation. The lunar surface preserves the most complete record of early solar system bombardment because the Moon lacks the geological processes that would erase or modify impact features over time. No plate tectonics recycle the lunar crust. No atmospheric weathering erodes crater rims. No volcanic resurfacing fills ancient basins with fresh lava flows. The craters that formed during the first billion years of lunar history remain essentially unchanged today, providing a fossil record of cosmic violence that extends back to the earliest phases of planetary evolution. The largest impact basins on the Moon: Aitken, Orientale, Imbrium, represent collisions with asteroids dozens of kilometers in diameter that excavated cavities hundreds of kilometers across. Earth experiences proportionally more impacts than the Moon due to its larger gravitational cross-section and stronger ability to focus incoming projectiles toward its surface. However, the geological activity that characterizes terrestrial evolution erases most evidence of early bombardment through crustal recycling, volcanic resurfacing, and erosional processes. Only the largest impact structures survive for billions of years, and even these become progressively more difficult to recognize as subsequent geological processes modify their original morphology. The absence of preserved early impact features on Earth creates a misleading impression of reduced bombardment compared to the heavily cratered lunar highlands. The source populations for early bombardment include both asteroidal and cometary objects scattered throughout the inner solar system by the gravitational perturbations of the growing giant planets. Jupiter's migration during the early phases of solar system evolution sends waves of debris spiraling inward toward the terrestrial planet zone, creating episodic increases in impact flux that may correlate with specific geological events preserved in the rock record. The composition of impacting bodies ranges from iron-rich metallic asteroids to volatile-rich comets, each contributing different chemical components to the evolving surfaces and atmospheres of Earth and Moon. The impact velocities during early bombardment exceed those observed for most contemporary cosmic collisions due to the highly eccentric and inclined orbits of debris scattered by planetary migration processes. Computer simulations suggest that typical impact speeds during the first few 100 million years of solar system history reached 20 to 30 kilometers per second, compared to average values of 15 to 20 kilometers per second for modern asteroid impacts. The higher velocities increase both the energy release per impact and the efficiency of shock melting and vaporization, creating more dramatic modifications to target surfaces and atmospheres. The thermal effects of large impacts contribute significantly to the surface temperature evolution of both worlds during the cooling phase following magma ocean crystallization. Individual impacts with asteroids larger than 10 kilometers in diameter can locally remelt substantial volumes of recently solidified crust, creating temporary magma lakes that require thousands of years to cool and crystallize. The cumulative heating from multiple large impacts may have been sufficient to maintain molten conditions in portions of both world surfaces for millions of years longer than would result from post-accretional cooling alone. The atmospheric consequences of impact bombardment prove particularly important for Earth's early climate evolution and volatile inventory. Large impacts can strip away substantial fractions of atmospheric mass through shock heating and hydrodynamic escape, while also contributing volatiles through the vaporization of cometary and hydrated asteroidal material. The balance between atmospheric loss and gain through impact processes depends on the size distribution and composition of impacting bodies, as well as the efficiency of atmospheric retention by Earth's gravitational field. The formation of impact melt sheets and breccias during large collisions creates distinctive rock types that preserve chemical and isotopic signatures of both target materials and impacting projectiles. These impact-generated rocks provide the only direct samples of early bombardment available for laboratory analysis, though their interpretation remains challenging due to the complex mixing and heating processes that occur during crater formation. The isotopic compositions of platinum group elements in impact breccias provide particularly valuable constraints on the types of asteroids and comets that dominated early bombardment. The seismic effects of large impacts propagate through the solid interiors of both worlds, creating earthquake-like disturbances that can trigger volcanic eruptions and landslides at considerable distances from impact sites. On the Moon, the seismic energy from basin-forming impacts may have fractured the crust on the far side of the satellite, creating preferential pathways for later basaltic volcanism that filled the impact basins with dark mare lavas. Earth's more active geology dissipates seismic energy more efficiently, but very large impacts still generate global earthquake swarms that persist for years after the initial collision. Scientists study the early bombardment history through the statistical analysis of crater size frequency distributions on both lunar and terrestrial surfaces, combined with theoretical models of debris evolution in the early solar system. The lunar crater record shows evidence for exponentially declining impact rates during the first billion years of solar system history, with possible superimposed spikes corresponding to discrete bombardment episodes. However, the interpretation of crater statistics remains complicated by the effects of secondary cratering, where debris from large impacts creates chains of smaller craters that can bias the apparent bombardment chronology. The mystery of the late heavy bombardment. A proposed episode of increased impact activity around 4 billion years ago remains one of the most controversial topics in early solar system evolution. Radiometric dating of lunar samples suggests that many large impact basins formed within a relatively narrow time window, implying either a discrete bombardment spike or sampling bias in the returned materials. The resolution of this controversy has important implications for understanding the timing of habitability on early Earth and the potential for life to emerge during periods of intense cosmic bombardment. The chemical contribution of impact bombardment to the volatile inventories of Earth and Moon depends critically on the composition of impacting bodies and the efficiency of volatile retention during high-energy collisions. Cometary impacts could have delivered substantial quantities of water and organic compounds to both worlds, though the extreme temperatures generated during hypervelocity impact would have destroyed most complex molecules. The net effect of bombardment on volatile budgets requires detailed modeling of impact processes and atmospheric escape mechanisms that remain poorly constrained for early solar system conditions. The transition from heavy bombardment to the more quiescent impact environment observed today reflects the gradual depletion of debris populations through collisional evolution and gravitational scattering processes. The clearing of the inner solar system creates increasingly stable orbital environments for the terrestrial planets, allowing the development of complex geological processes and ultimately biological evolution without the constant disruption of large impact events. The violence that characterizes the earliest phases of planetary evolution gradually gives way to the relative stability necessary for the emergence of complexity. The cratering record preserved on lunar and terrestrial surfaces provides a shared history of cosmic bombardment that links the evolution of both worlds to broader processes of solar system formation and evolution. The impacts that scar both worlds also deliver the chemical components necessary for geological differentiation and possibly biological evolution, demonstrating how destruction and creation operate simultaneously in planetary development. The cosmic collisions that threaten to sterilize developing worlds also provide the raw materials and energy sources that enable their continued evolution toward greater complexity. Ironically, The bombardment that creates thousands of craters on both worlds also erases evidence of earlier geological processes by repeatedly resurfacing and mixing crustal materials. The impact gardening of planetary surfaces destroys the sequential record of early geological evolution while simultaneously creating new rock types and chemical reservoirs that influence subsequent development. The cosmic violence that preserves some information about early solar system conditions also destroys other records, creating an incomplete and biased archive of planetary history that challenges scientific efforts to reconstruct the earliest phases of terrestrial and lunar evolution. The gradual slowing of Earth's rotation unfolds over millions of years through the persistent action of tidal friction, a process so subtle that no human lifetime could detect its effects, yet so inexorable that it fundamentally reshapes the dynamics of day and night on the planetary surface. When the Moon first coalesces from the debris of the giant impact, Earth spins on its axis once every 5 hours, creating a world where dawn and dusk succeed each other with the rapidity of a strobe light, where the Coriolis forces generated by rapid rotation dominate atmospheric circulation patterns, and where centrifugal acceleration at the equator approaches significant fractions of gravitational acceleration. The mechanism of tidal deceleration operates through the gravitational interaction between Earth's rotation and the Moon's orbital motion, mediated by the deformation of both solid and liquid materials on Earth's surface. The Moon's gravity creates bulges in Earth's oceans, atmosphere, and even solid crust that would remain aligned with the satellite if the planet were not rotating. However, Earth's rotation carries these tidal bulges slightly ahead of the Moon's position, creating a gravitational torque that acts to slow the planet's spin while simultaneously accelerating the Moon's orbital motion. The process resembles a cosmic brake system where Earth's rotational energy gradually transfers to lunar orbital energy through the medium of gravitational forces. The efficiency of tidal energy dissipation depends critically on the presence of liquid water on Earth's surface and the internal structure of both worlds. During the early phases of Earth-Moon evolution, when Earth's surface remains largely molten and the Moon orbits much closer to the planet, tidal friction operates with maximum efficiency. The liquid rock responds readily to tidal forces, flowing back and forth with each tidal cycle and converting kinetic energy into heat through viscous dissipation. As Earth cools and develops solid continents, tidal friction becomes concentrated in ocean basins where water can flow more freely than solid rock. The mathematical description of tidal evolution follows differential equations that couple Earth's rotational dynamics to the Moon's orbital mechanics through energy and angular momentum conservation laws. The rate of rotational deceleration depends on factors including the Moon's orbital distance, Earth's moment of inertia, the tidal quality factor that measures energy dissipation efficiency, and the distribution of mass within both worlds. Computer models integrating these equations backward in time suggest that Earth's rotation period has increased from its post-impact value of 5 hours to the current 24-hour day over the 4.5 billion year history of the Earth-Moon system. The changing length of Earth's day profoundly influences atmospheric and oceanic circulation patterns throughout geological time. Rapid rotation during the Hadean and Archean eons creates strong Coriolis forces that organize atmospheric flow into numerous small circulation cells rather than the large-scale patterns observed today. The faster rotation also enhances the strength of trade winds and jet streams, potentially affecting global climate patterns and the efficiency of heat transport between equatorial and polar regions. These circulation changes influence weathering rates, ocean chemistry, and ultimately the evolution of Earth's surface environment. The geological consequences of changing day length appear in the sedimentary record through tidal rhythmites-layered rock formations that preserve the cyclical patterns of ancient tides in shallow marine environments. These geological archives record not only the changing length of terrestrial days, but also the number of days per month and per year as the Moon's orbital period evolves simultaneously with Earth's rotation. Analysis of Precambrian tidal deposits suggests that Earth rotated significantly faster during the early phases of its history, supporting theoretical models of tidal evolution while providing quantitative constraints on the rate of change. The biological implications of Earth's slowing rotation extend throughout the history of life on the planet, influencing everything from circadian rhythms to evolutionary strategies. Organisms must adapt to progressively longer day-night cycles as Earth's rotation slows, creating selective pressures that favor flexible biological clocks capable of adjusting to changing environmental periodicities. The evolution of photosynthesis, daily vertical migration in marine organisms, and seasonal reproductive cycles all occur in the context of gradually lengthening days that provide different amounts of light and dark time throughout Earth's history. The Moon's outward orbital migration accompanies Earth's rotational deceleration as angular momentum transfers from the planet's spin to the satellite's orbital motion. The same tidal forces that slow Earth's rotation cause the Moon to spiral gradually away from the planet at a rate that averages approximately 3.8 centimeters per year, as measured by laser-ranging experiments using retroreflectors placed on the lunar surface by Apollo astronauts. This outward migration means that the Moon appeared larger in Earth's sky during earlier geological periods, creating more dramatic solar eclipses and stronger tidal effects in ancient oceans. The history of Earth's rotation rate influences the planet's magnetic field generation through its effects on convection patterns in the liquid iron core. Rapid rotation during Earth's early history enhances the Coriolis forces that organize convective flow in the core, potentially affecting the strength and stability of the geomagnetic field. Changes in magnetic field intensity over geological time may correlate with the evolution of Earth's rotation rate, though other factors, including core composition and thermal evolution, also influence magnetic field generation. Scientists study ancient rotation rates through multiple independent methods, including tidal rhythmites, coral growth patterns, and theoretical models of tidal evolution. However, significant uncertainties remain in extrapolating current tidal dissipation rates back through geological time due to changes in ocean basin geometry, continental configuration, and tidal resonance effects. The opening and closing of oceanic gateways, the formation and breakup of supercontinents, and the evolution of shallow shelf seas all influence tidal energy dissipation and complicate efforts to reconstruct Earth's rotational history. The mystery of tidal dissipation in the early Earth-Moon system includes the question of whether additional energy loss mechanisms operated during the first billion years of the system's evolution. Theoretical calculations based on current tidal dissipation rates suggest that the Moon should have migrated outward more slowly than appears consistent with geological constraints on early Earth-Moon dynamics. Either tidal dissipation was more efficient in the past due to different ocean configurations, or alternative mechanisms such as resonant interactions or temporary satellite systems contributed to the energy budget. The influence of solar tides on Earth's rotation provides a secondary but measurable effect that modulates the rate of rotational deceleration over long timescales. Although solar tides remain much weaker than lunar tides due to the Sun's greater distance, they create beat frequencies and resonance effects that can enhance or diminish the efficiency of tidal energy dissipation depending on the specific orbital configurations of Earth and Moon. These solar effects may have been particularly important during periods when the Earth-Moon system passed through tidal resonances that amplified the coupling between rotation and orbital motion. The paleontological record of growth patterns in marine organisms provides additional constraints on ancient day lengths through the analysis of daily growth increments preserved in shells, stromatolites, and other biological structures. Devonian corals show evidence for approximately 400 days per year, consistent with 22-hour days when combined with the known length of the Devonian year. Precambrian stromatolites suggest even shorter days during the earliest phases of Earth's history, though the interpretation of these ancient biological archives remains challenging due to preservation effects and environmental influences on growth rates. The evolution of Earth's rotation rate demonstrates how fundamental astronomical relationships change over geological time through the cumulative effects of small forces operating persistently over billions of years. The imperceptibly gradual slowing of Earth's spin exemplifies how planetary systems continue to evolve long after their formation, with ongoing dynamical processes reshaping the basic parameters that govern day length, tidal forces, and climate patterns. The moon that once raced across the sky in a matter of hours now requires a full day to return to the same position, marking time's passage through the changing rhythm of Earth's rotation. Ironically, the tidal forces that slow Earth's rotation and move the moon to more distant orbits also create the conditions necessary for the planet's long-term habitability and climate stability. The moon's gravitational influence stabilizes Earth's axial tilt against perturbations from other planets, preventing the extreme climate variations that would result from chaotic rotational dynamics. The gradually lengthening day provides increasingly stable environmental conditions that facilitate the evolution of complex life forms with sophisticated biological rhythms. The cosmic clockwork that emerges from the violence of planetary collision ultimately becomes the foundation for the temporal regularity that enables biological complexity to emerge and flourish on Earth's surface. The moon's slow retreat from Earth begins immediately after its formation, driven by the same tidal forces that govern the ebb and flow of terrestrial oceans, though operating on timescales so vast that human observation can barely detect the motion. Laser-ranging measurements to retroreflectors placed on the lunar surface by Apollo astronauts reveal that the moon currently recedes from Earth at a rate of 3.8 centimeters per year, roughly the same speed at which human fingernails grow. This seemingly insignificant motion accumulates over geological time into a migration of hundreds of thousands of kilometers, transforming the moon from a looming presence that filled a substantial portion of Earth's sky into the distant companion we observe today. The physics of lunar recession follows the principles of angular momentum conservation that govern all gravitational systems, though the specific mechanisms involve complex interactions between Earth's rotation, ocean tides, and the moon's orbital dynamics. As Earth's rotation slows due to tidal friction, the planet's rotational angular momentum decreases, while the moon's orbital angular momentum increases by an exactly compensating amount. This transfer of angular momentum occurs through gravitational torques generated by the tidal bulges that Earth's rotation carries slightly ahead of the moon's orbital position, creating a net force that accelerates the satellite's motion and causes it to spiral outward to higher, more energetic orbits. The rate of lunar recession varies significantly over geological time due to changes in tidal dissipation efficiency caused by evolving ocean basin geometry, continental configurations, and resonance effects. During periods when tidal oscillations in Earth's oceans approach resonant frequencies with basin dimensions, energy dissipation increases dramatically and the moon recedes more rapidly. Conversely, When ocean configurations favor minimal tidal friction, the recession rate slows to much lower values. Computer simulations suggest that the Moon's outward migration has proceeded episodically rather than smoothly, with periods of rapid recession alternating with intervals of slower evolution. The changing apparent size of the Moon in Earth's sky creates a fossil record of the satellite's orbital evolution that can be read in the geological archives of solar eclipses and tidal deposits. During the Archean Eon, when the Moon orbited approximately half its current distance from Earth, solar eclipses would have appeared dramatically different from modern eclipses, with the Moon's disk completely obscuring the Sun for much longer durations and covering much larger areas of Earth's surface. The ancient eclipse record, preserved in stromatolites and other sedimentary structures, provides quantitative constraints on the Moon's distance during specific geological periods. The gravitational effects of the receding Moon influence Earth's rotational stability and climate evolution throughout geological time. The Moon's gravitational torque on Earth's equatorial bulge stabilizes the planet's axial tilt against perturbations from other planets, preventing the chaotic variations in obliquity that would otherwise occur over timescales of millions of years. As the Moon moves to more distant orbits, its stabilizing influence weakens gradually, though calculations suggest that significant destabilization will not occur for several billion years when the Moon reaches distances exceeding 500,000 kilometers from Earth. The tidal effects of the more distant Moon also evolve predictably as the satellite recedes, with tidal forces decreasing according to the inverse cube of orbital distance. The dramatic tides that characterized Earth's early oceans when the Moon orbited much closer gradually diminished to the more modest tidal ranges observed today. This evolution affects everything from intertidal ecosystems to coastal erosion patterns, creating changing selective pressures for marine organisms and altering the efficiency of sediment transport in shallow seas. The energy source for lunar recession comes entirely from Earth's rotational energy, which decreases continuously as the planet's spin slows through tidal friction. The total energy budget for the Earth-Moon system declines over time as rotational kinetic energy converts to heat through tidal dissipation, with only a fraction of the lost energy appearing as increased orbital energy for the Moon. The remainder dissipates as heat in Earth's oceans and solid interior, contributing to the planet's thermal budget and influencing geological processes such as volcanism and tectonics. The mathematical description of lunar orbital evolution requires solving coupled differential equations that account for the changing efficiency of tidal dissipation as both orbital distance and Earth's rotation rate evolve. The equations include terms for energy loss through ocean tides, solid Earth tides, and atmospheric tides, each of which operates with different efficiency depending on the specific frequencies and amplitudes involved. The complexity of these interactions means that precise predictions of the Moon's future orbital evolution remain challenging despite the well-understood underlying physics. Scientists study the history of lunar recession through multiple independent approaches, including analysis of ancient tidal deposits, theoretical modeling of tidal evolution, and comparison with tidal dynamics in other planetary systems. The geological record provides snapshots of lunar distance at specific times in Earth's history, while theoretical models constrain the range of possible evolutionary pathways between these data points. However, significant uncertainties remain due to incomplete understanding of how tidal dissipation efficiency has changed as Earth's surface has evolved through plate tectonics and climate change. The mystery of enhanced tidal dissipation during certain periods of Earth's history challenges current understanding of the mechanisms responsible for lunar recession. Some geological evidence suggests periods of unusually rapid lunar recession that exceed the rates predicted by models based on current ocean configurations. These episodes may reflect temporary resonances between tidal oscillations and ocean basin dimensions, changes in ocean depth due to sea level variations, or alternative energy dissipation mechanisms that operated during specific geological intervals. The future evolution of the Earth-Moon system follows predictable trajectories based on the current understanding of tidal dynamics, though the timescales involved exceed the projected lifetime of the Sun as a main sequence star. The Moon will continue to recede until Earth becomes tidally locked to its satellite, showing the same face to the Moon just as the Moon currently shows the same face to Earth. This tidal locking will occur when Earth's rotation period equals the Moon's orbital period at approximately 47 current Earth days, with the Moon orbiting at a distance roughly 1.6 times its current value. The biological implications of the Moon's recession extend throughout the history of life on Earth and into hypothetical future evolutionary scenarios. Many marine organisms have evolved biological rhythms synchronized to lunar cycles, including spawning behaviors, migration patterns, and feeding strategies that depend on specific tidal conditions. As the Moon recedes and tidal effects weaken, these organisms must either adapt their behaviors or face extinction, creating ongoing evolutionary pressures that have operated throughout the history of complex life. The lunar recession also affects the long-term habitability of Earth by gradually reducing the stabilizing influence on the planet's rotational dynamics. Without the Moon's gravitational anchor, Earth's axial tilt would vary chaotically over timescales of millions of years, creating extreme climate variations that could challenge the survival of complex ecosystems. The satellite that forms through cosmic violence becomes essential for Earth's long-term climate stability, demonstrating how destructive events can create the conditions necessary for sustained habitability. The astronomical consequences of lunar recession influence phenomena ranging from eclipse frequencies to tidal heating in Earth's interior. As the Moon moves to more distant orbits, solar eclipses become less frequent and eventually cease entirely when the Moon's apparent diameter becomes smaller than the Sun's. The reduced tidal heating in Earth's interior may affect geological processes such as volcanism and plate tectonics. Though these effects remain small compared to other energy sources driving geological activity, the precision with which lunar recession can be measured and predicted demonstrates the power of gravitational physics to describe astronomical phenomena over vast ranges of time and space. The same mathematical principles that govern the Moon's orbital evolution also apply to planetary systems throughout the galaxy, providing insights into the long-term stability and habitability of terrestrial planets orbiting other stars. The cosmic dance between Earth and Moon serves as a laboratory for understanding gravitational dynamics that operate universally throughout the cosmos. Ironically, the Moon's retreat from Earth represents both the culmination and the ultimate dissolution of the partnership forged in the violence of the giant impact. The tidal forces that stabilize Earth's climate and enable the evolution of complex life also ensure the eventual separation of the two worlds, though over timescales so vast that the Sun will exhaust its nuclear fuel long before the process reaches completion. The gravitational embrace that creates the Earth-Moon system contains within it the seeds of its own dissolution, demonstrating how even the most fundamental astronomical relationships remain temporary arrangements in the context of cosmic time. Across the vast expanse of deep time, the Moon settles into its role as Earth's silent sentinel, its scarred face bearing witness to the cosmic violence that brought both worlds into existence while serving as a constant reminder of the creative power hidden within destruction. 4.5 billion years after the collision that formed it, the satellite continues its slow spiral away from Earth, carrying within its ancient rocks the isotopic signatures of two destroyed planets and preserving in its crater-covered surface the most complete record of early solar system bombardment available anywhere in the known universe. The Moon has become geology's Rosetta Stone, a key to deciphering the violent processes that shaped all terrestrial worlds during the chaotic epochs of planetary formation. The lunar highlands stretch across the satellite's surface like frozen seas of primordial rock, their pale anorthositic composition recording the chemical differentiation that occurred as the first global magma ocean slowly crystallized beneath the darkness of space. These ancient terrains preserve impact structures billions of years old, their circular rims and central peaks eroded only by the slow accumulation of micrometeorite dust and the occasional larger impact that creates fresh craters within the ghostly outlines of more ancient scars. The highlands represent some of the oldest solid surfaces in the solar system, unchanged witnesses to events that occurred when Earth itself remained largely molten and uninhabitable. The maria that fill the largest impact basins tell a different story, recording episodes of volcanic activity that occurred hundreds of millions of years after the Moon's formation, when radioactive decay and tidal heating maintained pockets of liquid rock within the satellite's cooling interior. These dark basaltic plains flowing across the lunar landscape like frozen lava lakes preserve the final major chapter of lunar geological activity, after which the satellite settled into the cold, geologically dormant state that characterizes its modern condition. The contrast between the ancient highlands and the younger maria creates the familiar pattern of light and shadow that humans have observed in the lunar disk for thousands of generations. The Moon's gravitational influence on Earth continues to operate with the same mathematical precision that has governed the system for billions of years, creating tides that rise and fall with clockwork regularity while gradually slowing the planet's rotation and driving the satellite's continued outward migration. Ocean tides carve coastlines and mix seawater, while atmospheric tides create subtle pressure variations that influence weather patterns and climate systems. The biological rhythms of countless organisms remain synchronized to lunar cycles, from coral spawning events timed to specific phases of the Moon to the nocturnal migrations of marine plankton that rise and fall with tidal currents. The stabilizing effect of lunar gravity on Earth's rotational dynamics provides one of the most crucial but invisible services that the satellite performs for its parent planet. Without the Moon's gravitational anchor, Earth's axial tilt would vary chaotically over timescales of millions of years, creating extreme climate variations that would challenge the survival of complex ecosystems and potentially prevent the evolution of intelligent life. The collision that nearly destroyed Earth also provides the gravitational stability that enables the planet's long-term habitability, demonstrating how catastrophic events can become foundational elements in the development of suitable conditions for life. The scientific legacy of lunar exploration extends far beyond the immediate goals of understanding Earth's satellite to encompass fundamental questions about planetary formation, the origin of life, and the likelihood of habitable worlds throughout the galaxy. Samples returned by Apollo missions provide ground truth for interpreting remote sensing data from other planetary bodies, while the detailed mapping of lunar geology serves as a template for understanding impact processes and early crustal evolution on all terrestrial planets. The Moon's airless surface preserves a geological record that extends back to the earliest phases of solar system history, offering insights into conditions that existed when life first emerged on Earth. The isotopic signatures preserved in lunar rocks continue to constrain models of the giant impact and subsequent evolution of the Earth-Moon system, providing quantitative tests of theoretical predictions about planetary collision dynamics and satellite formation processes. The near-identical oxygen isotope ratios in terrestrial and lunar samples confirm the thorough mixing of Earth and Theia material during the impact event, while subtle differences in other isotopic systems reveal details about the temperature and chemical conditions that prevailed during lunar formation. These geochemical fingerprints represent the only direct evidence available for studying planetary collisions, processes that remain beyond experimental reproduction in terrestrial laboratories. The cultural significance of the Moon in human civilization reflects its prominent position in Earth's sky and its obvious influence on terrestrial phenomena such as tides and the timing of seasons. Ancient astronomers used lunar phases to track the passage of time and develop the first calendars, while the satellite's regular motions provided early insights into the mathematical relationships that govern celestial mechanics. The Moon serves as humanity's first stepping stone into space and the testing ground for technologies that enable exploration of more distant worlds. From robotic missions that map planetary surfaces to human expeditions that demonstrate the possibility of survival beyond Earth's protective atmosphere, the future exploration of the Moon focuses increasingly on understanding its role as a recorder of early solar system conditions and a potential resource for supporting human expansion into space. The lunar poles harbor deposits of water ice that could provide both life support and rocket fuel for future missions, while the satellite's weak gravity and lack of atmosphere make it an ideal launching point for expeditions to Mars and the outer solar system. The Moon's far side, permanently shielded from Earth's radio emissions, offers unique opportunities for radio astronomy and the search for signals from extraterrestrial civilizations. The ongoing evolution of the Earth-Moon system continues to operate according to the same physical principles that have governed the partnership for billions of years, though the timescales involved exceed human comprehension and stretch far beyond the projected lifetime of the Sun as a stable star. The Moon will continue its gradual retreat from Earth until tidal forces bring both worlds into synchronous rotation, creating a double-planet system where each world shows the same face to its companion throughout their orbital dance around the dying Sun. The violence that created this cosmic partnership also programs its ultimate dissolution, though the process unfolds so slowly that it appears essentially eternal from any human perspective. The preservation of impact crater records on the Moon provides a unique archive of early solar system bombardment that extends back to the formation of the oldest surviving planetary surfaces. Unlike Earth, where geological activity continuously erases and recreates surface features, the Moon maintains a relatively complete record of cosmic collisions over the past 4 billion years. This cratering chronology serves as a calibration standard for dating surfaces throughout the solar system and provides crucial constraints on models of planetary migration and debris evolution during the earliest phases of solar system history. The chemical composition of the Moon reflects the extreme conditions that prevailed during its formation from the debris of planetary collision, with significant depletion in volatile elements and enrichment in refractory materials that survive the high temperatures of the impact environment. These compositional signatures provide insights into the processes that fractionate elements during planetary formation and the efficiency of volatile retention by terrestrial worlds. The Moon's bulk composition serves as a natural experiment in planetary chemistry under conditions that cannot be reproduced in terrestrial laboratories. The magnetic field history, recorded in lunar rocks, reveals details about the early evolution of planetary magnetic fields and the processes that generate magnetism in terrestrial worlds. Although the Moon lacks a global magnetic field today, paleomagnetic studies of Apollo samples suggest that the satellite possessed a substantial magnetic field during its early history, possibly generated by convection in a liquid iron core or by external magnetic fields associated with the early Earth. The timing and intensity of lunar magnetism provide constraints on thermal evolution models and core formation processes in small planetary bodies. The Moon's role as a natural laboratory for understanding planetary processes extends to studies of space weathering, impact mechanics, and the physics of airless bodies throughout the solar system. The lunar surface provides the most accessible example of how cosmic radiation, micrometeorite bombardment, and thermal cycling modify planetary surfaces over geological time. These space weathering processes affect the spectral properties and physical characteristics of airless bodies throughout the solar system, from asteroids to the moons of the outer planets. In the grand context of cosmic evolution, the moon represents both a monument to destruction and a testament to creation, preserving within its ancient rocks the memory of the violence that shaped the early solar system, while serving as the gravitational anchor that enables Earth's long-term habitability. The satellite born from cosmic collision becomes the silent guardian of terrestrial stability. Its presence in Earth's sky, a constant reminder that destruction and creation remain inseparably linked in the ongoing evolution of planetary systems. The moon's scarred face bears witness to 4.5 billion years of cosmic history, while its gravitational influence continues to shape the world that gave it birth, demonstrating how the consequences of singular events can persist across the vast expanses of deep time. The story settles now into the quiet rhythm of geological time, where moments stretch into millennia and the urgent violence of creation gives way to the patient persistence of gravitational forces. Earth and Moon continue their ancient dance, locked in orbital embrace, yet slowly, imperceptibly drifting apart. Their partnership carved from collision and maintained through the subtle mathematics of tidal friction. The satellite that once filled Earth's sky like a second sun now hangs at a distance that renders it small enough to be covered by an outstretched thumb, its apparent shrinking a measure of time's passage across eons too vast for human minds to fully grasp. In the silence of space, the moon keeps its vigil. One face forever turned toward Earth, while the other remains hidden in permanent mystery. Its surface tells stories written in the language of craters and maria, highlands, and rills, each feature a sentence in the longer narrative of solar system evolution. The scars that mark its face record impacts that occurred when Earth's surface still glowed with the heat of formation, when no life stirred anywhere in the cosmos, when the very concept of biology remained billions of years in the future. The tides that rise and fall in Earth's oceans carry within their rhythm the memory of that first collision, the angular momentum transferred from planetary destruction to orbital motion, now expressed in the gentle lifting and lowering of seawater against shorelines around the globe. Each tide represents a small dissipation of energy, a tiny fraction of rotational momentum converted to heat and radiated away into space, contributing to the moon's gradual retreat across distances measured in the breadth of atoms but accumulated over the breadth of geological time. The partnership forged in violence has become the foundation for stability. The cosmic accident that nearly destroyed Earth transformed into the gravitational anchor that maintains the planet's climate within narrow bounds suitable for the emergence and evolution of life. The moon's presence steadies Earth's axial tilt against the perturbations of other worlds, preventing the chaotic climate variations that would challenge the survival of complex ecosystems and the development of intelligence capable of understanding its own cosmic origins. In laboratories around the world, scientists continue to decode the chemical messages preserved in lunar samples, reading isotopic signatures like letters from the distant past that describe conditions during the first moments of the Earth-Moon system. Each measurement reveals new details about the temperatures and pressures that prevailed during satellite formation, the efficiency of chemical mixing in the debris disk, the timeline of cooling and crystallization that established the basic architecture of both worlds. The moon drifts onward through space, carrying its cargo of ancient secrets toward a future where it will hang even smaller in Earth's sky, where its tidal influence will weaken further, where the eclipse shadows it casts will no longer fully cover the solar disk. The satellite moves toward a destiny written in the equations of celestial mechanics, following orbital paths that unfold with the inevitability of mathematical law across timescales that dwarf the lifetime of species, continents, and perhaps even worlds. Rest now in the knowledge that the cosmic violence that brought these worlds together operates according to principles that create as much as they destroy. That the collision that nearly ended Earth's story also wrote the opening chapters of everything that followed. The moon hangs in darkness, patient and eternal, a witness to deep time and a guardian of terrestrial stability. Its presence a gentle reminder that even in the vastness of space, some partnerships endure across the infinity of cosmic time. Sleep well, knowing that the gravitational dance continues overhead, that tides will rise and fall with mathematical precision, that the moon will keep its ancient watch while Earth turns slowly beneath the stars. The story of worlds colliding and moons forming belongs to deep time, but its consequences reach into every tide pool and every night sky, connecting the violence of planetary birth to the gentle rhythms that mark the passage of terrestrial days and seasons. The moon waits in silence, carrying forward the memory of two destroyed worlds, a monument to the creative power hidden within destruction, a testament to the persistence of gravitational partnerships across the vast expanse of cosmic time.